Every moment, our universe expands. What sparked the birth of this cosmos and what forces hold it together? Join us as we delve into the mysteries of dark matter and dark energy, two invisible entities that shape our reality yet remain unknown. According to the Big Bang theory, the universe began as a singular point, extremely hot and incredibly dense, around 14 billion years ago. Imagine a balloon that is fully deflated. At this moment, it represents the entirety of the universe, compacted into an incredibly tiny space. Then, in an instant, this tiny point exploded, not in the sense of an explosion we might envision, but more like an expansion where everything suddenly began to stretch and grow outward. As this expansion occurred, the universe cooled down. The first tiny particles began to form, and as temperatures dropped, these particles combined to create simple elements like hydrogen and helium. Over time, these elements clumped together due to gravity, forming clouds that eventually birthed the stars and galaxies we know today. The universe continued to expand and cool, leading to a complex evolution filled with various structures. This theory is supported by several observations like the cosmic microwave background radiation, which is a faint glow left over from the early universe, and the discovery that galaxies are moving away from us, suggesting that the universe is still expanding. This continuing expansion is similar to how the surface of the balloon stretches as it inflates. Thus, the Big Bang theory provides a framework for understanding not only how the universe began, but also how it continues to evolve and change over time. The theory of the Big Bang, which describes the origin of our universe, is supported by several key pieces of evidence. First, we can observe that galaxies are moving away from us in all directions, suggesting that the universe is expanding. This observation aligns with what we expect if space itself originated from a singular, incredibly dense point spreading out over time. Next, we find a faint background radiation permeating the universe, known as cosmic microwave background radiation. This radiation is almost uniform throughout the sky and is thought to be the leftover heat from the hot, dense state of the early universe, cooling down as the universe expanded. Scientists estimate this radiation dates back to when the universe was just a few 100,000 years old, providing a snapshot of the very early moments after the Big Bang. Additionally, the abundance of light elements like hydrogen and helium in the universe supports the Big Bang theory. This production of elements took place during the first few minutes after the explosion in a process called nucleosynthesis, where these light elements formed as the universe cooled. Lastly, the large-scale structure of the universe, such as galaxies and clusters, provides further evidence. The distribution and formation of galaxies align with computer simulations based on the Big Bang model, demonstrating how matter clumped together over billions of years since the initial explosion. Together, these observations build a robust framework that supports the idea that our universe began with the Big Bang, allowing us to understand both its origins and its development over time. In the moments right after the Big Bang, the universe was extremely different from what we know today. It was a hot and dense state, almost like a fiery explosion of energy and particles. Picture a small region of space filled with an unimaginable amount of heat. During this time, temperatures soared to levels that are hard to comprehend, where even the simplest forms of matter couldn't hold together. Initially, the universe consisted mainly of fundamental particles, such as protons, neutrons, and electrons, along with a sea of energy. These basic building blocks didn't come together to form atoms yet, because the overwhelming energy caused them to move rapidly and collide with each other. This also meant that light couldn't travel freely. It was constantly being absorbed and re-emitted by those energetic particles. As the universe began to expand, it started to cool down. This cooling allowed the particles to lose energy and eventually start to form simple atoms, mainly hydrogen and helium. This transition was crucial for the universe's evolution. For several minutes after the Big Bang, this process continued, forming the first nuclei in a period known as nucleosynthesis. While this was happening, the universe was still chaotic and full of radiation. It was not until about 300,000 years later that conditions became stable enough for light to travel freely. When that happened, the universe became transparent for the first time, allowing photons to move across the cosmos. This marked the beginning of what we now see as the cosmic microwave background radiation. the afterglow of that intense initial explosion providing a snapshot of the early universe. Scientists estimate the age of the universe using several interconnected methods, each shedding light on this vast question. At the heart of their calculations is the concept of the expansion of the universe. Imagine the universe as a balloon being inflated. As it expands, points on the balloon, representing galaxies, move farther apart. By observing how fast these galaxies are receding from us, scientists can backtrack this expansion to determine when everything was together, which is referred to as the Big Bang. To measure this expansion, scientists use a special type of light called redshift. When light from distant galaxies travels to us, it shifts towards the red end of the spectrum as those galaxies move away. This shift provides vital information about their speed and, consequently, how long ago they started moving apart. Another key method involves studying the oldest known stars. By looking at their brightness and chemical makeup, astronomers can gauge their age. This data is used to understand how long stars have been forming since the early days of the universe. The oldest stars provide a timeline that helps researchers piece together the universe's history. Additionally, the cosmic microwave background radiation plays a significant role. This faint glow, which fills the universe, is a remnant of the heat from the Big Bang. By analyzing its detailed properties, scientists can glean insights into the conditions of the early universe, further refining their estimates of its age. When all these methods converge, they suggest that the universe is about 13.5 billion years old. Each research perspective contributes to this understanding, creating a comprehensive picture of our cosmic timeline. Through the harmony of these scientific approaches, we draw closer to unraveling the mysteries of the universe's vast beginnings. The Big Bang theory is the most widely accepted explanation for the origin of the universe, but several alternative theories challenge or expand upon it. One of the most intriguing concepts is the steady-state theory. This idea suggests that the universe has always existed as it is today, with new matter being continuously created to fill the gaps left by galaxies moving away from one another. In this view, the universe is eternally unchanging and infinite in both time and space, which contrasts sharply with the dynamic and evolving picture painted by the Big Bang. Another alternative is the cyclic model, which posits that the universe undergoes endless cycles of expansion and contraction. According to this theory, the universe expands after each Big Bang and eventually slows down, collapsing back in on itself in a big crunch, only to explode again in another bang. This cycle of rebirth creates an eternal loop of universal life, where time is not just linear but cyclical. In addition, the multiverse theory suggests that our universe might be just one of many universes existing simultaneously, each with its own origins. In this view, different universes could arise from various processes, including random fluctuations in energy, leading to a diversity of physical laws and structures. Some scientists even propose the idea that our universe began as a small patch within a larger cosmic landscape, giving rise to multiple realities, each with unique characteristics. These alternative theories provide fascinating perspectives on the universe's origins. They invite us to ponder deeper questions about reality itself, challenging our understanding of time, space, and existence. While the Big Bang theory remains prevalent, exploring these alternatives widens our horizons and emphasizes the complexity of cosmic beginnings. Dark matter is a fascinating and elusive substance that makes up a significant portion of the universe's total mass. Imagine adding invisible bricks to a building. Even though you can't see the bricks, they greatly influence how the structure stands and functions. Similarly, dark matter does not emit light or energy, making it invisible to our current instruments. We cannot see it directly, instead we know it's there because of its effects on galaxies and clusters of stars. Scientists first noticed dark matter's influence when they observed that galaxies were spinning much faster than expected. If only visible matter were present, these galaxies would fly apart due to the speed at which they rotate. However, they stay intact, suggesting that there is additional unseen mass, dark matter, providing the necessary gravitational pull to hold them together. The mystery of dark matter lies in its undetectable nature. Despite extensive studies and indirect evidence pointing to its existence, we have yet to identify what dark matter is made of. Many theories suggest it could be composed of unique particles that don't interact with light or normal matter like anything we encounter in our everyday lives. Some scientists even propose it might consist of exotic forms of matter that defy our understanding of physics. This unknown aspect adds to the enigma of dark matter, driving scientists to explore various possibilities through experiments and astronomical observations. As they delve deeper, the quest to unravel the secrets of dark matter not only promises a greater comprehension of the universe, but also challenges our fundamental concepts of what the cosmos is made of. Dark matter plays a crucial role in shaping the structure and dynamics of galaxies. While it cannot be seen directly, dark matter is believed to make up a significant portion of the universe's total mass. Think of it as an invisible framework that holds galaxies together. When galaxies form, they are drawn together by gravity. Regular matter, which makes up stars, planets, and gas, is not enough to explain the movements we observe in galaxies. For instance, scientists have noticed that stars at the edges of galaxies are moving much faster than would be expected based only on the visible matter present. This discrepancy suggests that there is much more mass present, exerting additional gravitational forces. Dark matter creates a gravitational halo around galaxies. This halo provides the gravitational pull necessary for galaxies to form and hold their shape. It ensures that once these magnificent structures develop, their stars and other contents remain bound within them, preventing them from flying apart. Furthermore, dark matter influences how galaxies interact with one another. When two galaxies approach each other, the dark matter halos can lead to complex gravitational interactions, sometimes resulting in beautiful mergers. These events can trigger the formation of new stars, altering the galaxy's appearances and behaviors fundamentally. Dark matter acts as an unseen architect, guiding the assembly of galaxies and assuring their stability, ultimately helping to define the vast cosmic landscapes we observe today. Its mysterious presence showcases how much we still have to learn about the universe. Dark matter is one of the biggest mysteries in our universe. While it cannot be seen directly, scientists know it exists because of its effects on galaxies and cosmic structures. The main leading hypotheses about the composition of dark matter revolve around a few key ideas. One prominent hypothesis suggests that dark matter is made up of particles that are different from those that compose ordinary matter, such as atoms. These particles are known as weakly interacting massive particles, often abbreviated to WIMPs. The name comes from their expected size and the fact that they interact very weakly with regular matter, making them nearly invisible to traditional detection methods. If these particles exist, they would cluster around galaxies, contributing to the gravitational forces that hold them together. Another possibility is that dark matter consists of axions, which are hypothetical particles thought to be very light and similarly weakly interacting. Scientists are exploring this idea because axions could also help solve other puzzles in physics, like the behaviors observed in certain high-energy particle interactions. There's also a theory suggesting that dark matter could be made up of primordial black holes. These are small black holes that might have formed soon after the Big Bang. Unlike typical black holes that form from dying stars, primordial black holes could vary in size, and their existence would account for some of the gravitational effects we see without needing additional particles. Some researchers are investigating modified theories of gravity as potential explanations, which propose that our current understanding of gravity needs adjustments, rather than relying solely on dark matter to explain the movements of galaxies and galaxy clusters. While all these ideas remain under investigation, the quest to uncover the true nature of dark matter continues. Each hypothesis offers a different perspective, and as technology advances, scientists are getting closer to finding concrete evidence to understand what dark matter really is. Detecting dark matter is one of the great challenges in modern astronomy and physics because it does not emit light or energy that we can observe directly. Instead, scientists rely on its gravitational effects. Imagine a bustling city where you cannot see the buildings but can observe how people move in response to their presence. Similarly, scientists observe how galaxies behave and how they are structured. One way they do this is by studying the rotation of galaxies. When we look at a galaxy, we can see how fast it is spinning. According to our understanding of gravity, if we only account for the visible stars, the rotation should be much slower. However, galaxies spin at surprising speeds, implying that there is additional unseen mass exerting its gravitational influence. This unseen mass is thought to be dark matter. Another method involves observing galaxy clusters. When these clusters form, they contain far more mass than what is visible. Scientists employ various techniques to measure the gravitational effects on light from background objects. As light passes near these clusters, it bends. This bending, or gravitational lensing, gives clues about the mass present in the cluster, including dark matter. Additionally, scientists analyze the cosmic microwave background, which is the afterglow of the Big Bang. Variations in temperature across this background light give insights into the distribution of matter, including dark matter, in the universe. Combining these observations allows researchers to piece together a picture that supports the existence of dark matter, even though it remains invisible to our instruments. Through these methods, researchers create a map that reflects the influence dark matter has on the universe, revealing that, although it cannot be seen, its presence is felt throughout the cosmos. Dark matter, an elusive substance that makes up a significant portion of the universe's mass, yet does not emit light, remains one of the great mysteries in astrophysics. Currently, scientists around the world are conducting various experiments to uncover its secrets. One major line of research involves sensitive detectors placed deep underground, shielded from cosmic rays and other interference. These detectors aim to catch the rare interactions of dark matter particles with ordinary matter. In laboratories, researchers use advanced technologies to create conditions that might allow dark matter particles, if they exist, to collide with atomic nuclei. By analyzing the energy and patterns of any resulting signals, scientists hope to identify unique signs of dark matter. Another approach involves observing the universe on a grand scale. Huge telescopes are searching for the effects of dark matter on the motion of galaxies and the shape of galaxy clusters. When light from distant galaxies passes near massive clusters, it bends due to gravity, a phenomenon known as gravitational lensing. This bending reveals how dark matter is distributed, even though it cannot be seen directly. Space missions, like those aiming to measure cosmic microwave background radiation, also provide clues. This faint afterglow from the Big Bang contains information about the early universe that can hint at the influence of dark matter on cosmic formation processes. Finally, particle colliders are testing theories related to dark matter. By smashing particles together at high speeds, these experiments may produce new, heavier particles that could be candidates for dark matter. Each of these lines of inquiry brings us closer to a clearer picture of this hidden, yet influential component of our universe. The journey to uncovering dark energy began in the late 20th century when astronomers were studying distant supernovae, which are massive explosions of dying stars. These supernovae serve as cosmic beacons, allowing scientists to measure distances in the universe. As researchers observed the light from these explosions, they expected it to fade in a predictable way based on how the universe was expanding. Surprisingly, the data showed that the light from these distant supernovae was dimmer than anticipated. This unexpected dimming indicated that the universe was not just expanding, but that this expansion was accelerating. This meant something must be pushing the galaxies apart at an increasing rate, counteracting the gravitational forces that would normally slow them down. To explain this phenomenon, scientists coined the term dark energy. While we do not know exactly what dark energy is, we understand that it makes up a significant portion of the universe's total energy content. It acts like a kind of energy that fills space and has a negative pressure, which is driving this acceleration. Dark energy helps explain why galaxies, instead of slowing their outward movement, are racing away from each other. This discovery has profound implications for the fate of the universe. If dark energy continues to dominate, it suggests that the universe will keep expanding forever, leading to a scenario known as the Big Freeze, where galaxies drift apart and stars slowly burn out. Thus, the realization of dark energy not only transformed our understanding of cosmic expansion, but also raised important questions about the ultimate destiny of everything we observe in space. Dark energy and dark matter are two of the most intriguing components of our universe, and they play distinctly different roles. Dark matter is like an invisible glue that holds galaxies together. Although it cannot be seen directly, its existence is inferred from the way galaxies rotate and the way light from distant objects bends as it passes nearby. We can think of dark matter as a type of cosmic scaffolding that provides the necessary mass for gravity to influence visible matter, ensuring that stars stay bound within galaxies and galaxies remain clustered together. In contrast, dark energy is a mysterious force that drives the accelerated expansion of the universe. Imagine stretching a rubber band. As it pulls apart, the distance between 2 points increases. Dark energy works similarly, pushing galaxies apart more rapidly than before. It exerts a kind of negative pressure, counteracting the gravitational forces trying to pull things together. While dark matter contributes to the structure and stability of the universe, dark energy affects its overall shape and future. To sum up, dark matter is about keeping things together, while dark energy is about the universe stretching further apart. Both are elusive, making up a significant portion of the total universe composition, yet they operate in fundamentally different ways that challenge our understanding of physics. Dark energy is a mysterious force believed to be driving the accelerated expansion of the universe. To understand how it works, imagine blowing up a balloon. As you blow air into it, the rubber stretches and the surface expands outward. In the same way, the universe is getting bigger, but instead of air, dark energy acts like a constant push that causes this expansion to speed up. After the Big Bang, matter pulled everything together with gravity, leading to a slowing expansion. However, around a few billion years ago, observations showed a surprising twist. The universe began expanding faster instead. This shift suggests that a powerful force, which we call dark energy, was at play. Unlike ordinary matter, which clumps together and exerts gravitational force, dark energy seems to have a uniform presence throughout space. It triggers a repulsive effect, countering the gravitational pull of galaxies and cosmic structures. As a result, this force not only maintains the universe's expansion, but accelerates it. Scientists speculate that dark energy makes up about 70% of the total energy content of the universe, meaning it profoundly influences cosmic dynamics. Despite its significance, dark energy remains largely mysterious. It's a key piece in understanding our universe's fate. Current theories suggest that if its influence continues, galaxies will move further apart, leading to a future where stars and galaxies become isolated, making the universe appear darker over time. Understanding dark energy helps us grasp not only how the universe is expanding, but also what lies ahead in its vast, intricate timeline. Understanding dark energy presents significant challenges for scientists, primarily because it is one of the greatest mysteries of our universe. While we can observe its effects, its true nature remains elusive. Dark energy is believed to be responsible for the accelerated expansion of the universe, pushing galaxies away from each other at an increasing rate. However, this is a conceptual leap, as dark energy has not been directly observed or measured. One key challenge lies in its invisibility. Unlike objects that emit or reflect light, dark energy does not interact with electromagnetic radiation, making it impossible to observe directly with telescopes. Instead, scientists infer its existence through observations of distant supernovae and the cosmic microwave background, ancient light remnants from the birth of the universe. These observations suggest that the universe's expansion is accelerating, but they do not provide direct insight into what dark energy actually is. Additionally, there is a lack of understanding regarding how dark energy fits into the framework of fundamental physics. Existing theories of gravity, formulated by Isaac Newton and Albert Einstein, do not adequately explain this phenomenon. Scientists must grapple with reconciling dark energy with established theories, which makes formulating and testing new hypotheses very complex. The sheer scale of the universe also adds to the difficulty. Researchers must gather data from vast distances and timescales, increasing the uncertainty in their measurements. As they study cosmic structures, they encounter many variables that can influence their results, complicating the task of isolating dark energy's effects. Lastly, the diversity of theories attempting to explain dark energy further complicates the situation. From concepts of a cosmological constant which suggests dark energy as a fundamental property of space, to more dynamic models that evolve over time, the scientific community faces a multitude of ideas, each requiring rigorous testing and validation. Scientists face a daunting task in untangling the web of observations, theories, and unknowns surrounding dark energy, as they strive to uncover the truth behind this enigmatic force shaping our universe. Know them. With a clearer grasp of dark energy, theories about the ultimate fate of the universe could shift dramatically. We might learn whether the universe is destined to continue expanding forever, collapse back in on itself, or reach a stable state. Such revelations could provoke philosophical and scientific discussions about our place in the universe, reshaping humanity's understanding of existence itself. Additionally, gaining knowledge about dark energy may also inspire advancements in technology and methods of exploration. By understanding how this force operates, we might develop innovative ways to observe the universe and gather data on distant galaxies, potentially leading to discoveries we have yet to even imagine. Solving the mystery of dark energy is not merely an academic exercise. It could fundamentally alter our perception of reality, expanding our horizons and deepening our connection to the cosmos. The implications would reach far beyond science, influencing everything from philosophy to our collective future as we strive to understand our universe more deeply. Dark energy is one of the most intriguing puzzles in modern astrophysics. It makes up about 70% of the universe, yet its true nature remains elusive. Currently, we understand dark energy as a force that drives the accelerated expansion of the universe. Imagine the universe as a balloon being blown up. The more air you add, the faster it expands. Dark energy acts like that air, pushing all galaxies apart and causing the universe to stretch ever further. If we successfully solve the mystery of dark energy, it could completely change how we view the cosmos. For instance, understanding dark energy might reveal new laws of physics, reshaping our understanding of forces and how they interact on a cosmic scale. This could lead to groundbreaking insights about the creation of the universe, the formation of galaxies, and even the fate of the cosmos itself. Moreover, unlocking the secrets of dark energy might illuminate the relationship between energy, matter, and the fabric of space-time. This could lead to profound insights into the beginnings of the universe, perhaps even redefining concepts of time and space as we. A black hole is a region in space where gravity pulls so strongly that nothing can escape from it, not even light. This immense gravitational force arises from the collapse of a massive star. Essentially, when a star exhausts its nuclear fuel, it can no longer support its own weight. If the star is sufficiently massive, it will undergo a supernova explosion, which blows off its outer layers. What remains is the core, which can continue to collapse under its own gravity. As the core contracts, it forces all its mass into an incredibly small space. This process creates an intense gravitational field, resulting in the formation of a black hole. The boundary surrounding this region, the point of no return where escape becomes impossible, is known as the event horizon. Once something crosses this boundary, it is inexorably drawn into the black hole. Interestingly, black holes come in different sizes. Stellar black holes are formed from individual stars, while supermassive black holes, found at the centers of galaxies, have masses millions or even billions of times greater than the Sun. Their formation is still a topic of research, but they could arise from the merging of smaller black holes or the direct collapse of massive gas clouds in the early universe. Black holes represent one of the universe's most fascinating phenomena, revealing just how extreme the laws of physics can be. The event horizon is a crucial boundary surrounding a black hole. Imagine a dark point in space where the force of gravity is so intense that nothing, not even light, can escape once it crosses this boundary. It marks the point of no return. If an object ventures inside the event horizon, it will be pulled inexorably toward the center of the black hole, a region known as the singularity, where gravity is thought to become infinite. This boundary holds significant importance for several reasons. First, it defines the limits of our observable universe regarding a black hole. Anything that crosses the event horizon becomes invisible to outside observers because no information can come back to us. This makes the event horizon a fascinating puzzle for scientists, highlighting the mysteries of gravity and the nature of space and time. Moreover, the event horizon plays a role in understanding how black holes interact with their surroundings. It affects the behavior of matter and energy near a black hole, influencing the formation of accretion disks, rings of gas and dust that swirl around black holes before getting drawn in. Additionally, the study of the event horizon leads to questions about fundamental physics, such as the nature of gravity, the laws of thermodynamics in extreme settings, and even ideas about the potential existence of parallel universes. Scientists use highly sensitive detectors to capture these minute differences, almost like an artist identifying strokes in a painting. Once the data is collected, researchers meticulously analyze it using advanced computer models. They look for patterns that reveal how matter and energy were distributed across the universe so long ago. This process also involves comparing observations with theoretical predictions made by cosmological models, allowing scientists to refine their understanding of fundamental questions, such as the rate of the universe's expansion and the nature of dark matter and dark energy. Through this careful study, scientists reconstruct a picture of the universe's infancy, enhancing our understanding of how it evolved into the cosmos we observe today. The cosmic microwave background is not just background noise, it is the oldest light we can see, and its study is crucial for unlocking many mysteries about the universe's origins. Cosmic radiation, particularly the cosmic microwave background radiation, serves as a crucial tool for testing cosmological models. This radiation is like a faint afterglow from the early universe, akin to a snapshot taken when the universe was only a few 100,000 years old. By studying it, scientists can glean important information about the universe's origin, composition, and evolution. Think of this radiation as a relic, carrying information about the conditions that existed just after the Big Bang. As it travels through space, it leaves traces of the density fluctuations that occurred in those early moments. These fluctuations are pivotal because they eventually led to the formation of galaxies and larger structures we see today. By analyzing the patterns and temperature differences in this radiation, researchers can validate or challenge theoretical models about how the universe expanded and evolved. Moreover, different cosmological models predict varying amounts and patterns of such radiation. When scientists compare their observations of cosmic microwave background radiation with predictions made by models, they can assess which theories hold up under scrutiny. Differences in expected versus observed data can lead to revisions of existing models or even prompt entirely new theories. Essentially, this radiation acts as a cosmic messenger, informing us about the very fabric of the universe and helping us refine our understanding of fundamental concepts such as dark matter, dark energy, and the rate of cosmic expansion. It is a central piece of the puzzle in the quest to understand the universe's history and its future. The universe, when viewed on a grand scale, is a vast and complex tapestry of structures devoid of any simple form. At its largest levels, it resembles a web, woven from galaxies and clusters of galaxies that form an intricate pattern through vast stretches of emptiness known as voids. Galaxies are not scattered randomly, instead they are grouped together in clusters, which can contain hundreds to thousands of them, held together by gravity. Beyond these clusters, there are superclusters that consist of several clusters of galaxies, all interconnected by filaments of dark matter, a mysterious substance that does not emit light but influences the gravitational forces within the universe. This structure plays a crucial role in how galaxies interact and move across the cosmos. As you zoom out even further, you encounter enormous voids, the largest gaps in this cosmic web that can be billions of light-years across, where few galaxies reside. These voids form a significant part of the universe, showcasing the contrast between the dense regions filled with galaxies and the emptiness that separates them. Additionally, the universe is expanding. This means that galaxies are moving away from each other over time. This expansion causes the fabric of space itself to stretch, creating more distance between distant galaxies. As a result, the universe appears to be growing larger, a phenomenon that has intrigued scientists since its discovery in the early 20th century. Overall, the large-scale structure of the universe is a remarkable interplay of density and emptiness, connecting everything with gravitational threads that bind galaxies, clusters, and vast voids into one magnificent cosmic web. Cosmic filaments are vast structures in the universe, resembling a web that stretches across the cosmos. Imagine looking at a gigantic spider's web where the strands are composed of galaxies and dark matter. These filaments represent the largest known scale of cosmic organization, playing a critical role in the formation and distribution of matter in the universe. At the heart of this grand design are the clusters of galaxies that sit at the intersections of these filaments, while the filaments themselves act as the highways through which matter flows. Over billions of years, gravity pulls gas and dark matter into these threads, leading to the formation of stars and galaxies along their lengths. This process creates a vast network that can range from filamentary structures that are millions of light-years long to smaller ones that are only a fraction of that size. Cosmic filaments are part of a larger framework known as the cosmic web, which outlines how galaxies and clusters are interconnected in 3 dimensions. The structural arrangement includes not only filaments but also voids, vast empty regions that contain very few galaxies. Understanding this web is crucial for astronomers, as it helps explain both the large-scale structure of the universe and the dynamics of galaxy formation and evolution. Cosmic filaments serve as the backbone of the universe, illustrating how galaxies are distributed through intricate, ever-expanding patterns shaped by the forces of gravity and the unseen influence of dark matter. Galaxies are not scattered randomly throughout the universe. They are organized in a complex and fascinating structure. Imagine the universe as a vast web. Within this web, galaxies form clusters, which are groups of hundreds to thousands of galaxies held together by gravity. These clusters can be found in larger collections known as superclusters. Superclusters can stretch over immense distances, often containing multiple clusters and thousands of galaxies packed together. Between these clusters and superclusters, there are vast empty spaces called cosmic voids. These voids can be thought of as the regions of the web where there are very few galaxies. Further, when we zoom out and look at the big picture of the universe, we find that galaxies tend to be arranged in long, thin filaments and walls. This structure results from the early universe's conditions and the gravitational forces acting on matter over billions of years. The gravitational pull of nearby galaxies influences their motion, leading to this organized arrangement. As we study this cosmic layout, we discover that it reflects the universe's history, showing where matter clumped together in the moments after the Big Bang. The motion and distribution of galaxies not only enhance our understanding of the universe's evolution, but also provide clues about dark matter and dark energy, 2 mysterious components that shape our universe but remain challenging to understand fully. The universe is filled with vast clusters of galaxies, and these celestial gatherings hold many mysteries about their formation and evolution. At their core, galaxy clusters consist of hundreds to thousands of galaxies bound together by gravity, along with hot gas and dark matter. One of the primary mysteries is how these clusters initially formed. Scientists believe that in the earlier stages of the universe, tiny fluctuations in density created the seeds from which clusters grew, but the exact mechanisms of this growth are still not fully understood. Another intriguing aspect is the role of dark matter in cluster formation. Dark matter makes up a significant amount of the universe, yet it does not emit light, making it difficult to study directly. Its presence is inferred through gravitational effects. The relationship between visible matter, like stars and galaxies, and invisible dark matter in clusters poses many questions. How do these 2 components interact over time? Understanding this relationship could unveil essential details about the universe's structure. Further complicating the picture is the evolution of clusters. Over billions of years, they change significantly, sometimes merging with other clusters or undergoing processes known as hierarchical growth, where smaller structures combine to form larger ones. The dynamics of these mergers can lead to immense energy releases, observable as shocks in the hot gas surrounding the galaxies. Scientists are eager to understand how frequently these events occur and their impact on the evolution of the galaxies within the clusters. Moreover, the distribution of galaxies within clusters can also be puzzling. Some galaxies appear to be spinning rapidly, while others seem to be moving toward their cluster's center. This diversity raises questions about the history of each galaxy and the environment's influence on their formations. Lastly, ongoing research is investigating the role of cosmic events, like supernovae and their explosions, in shaping the gas surrounding galaxy clusters. These explosions might change the temperature and density of the gas, which can affect galaxy growth and behavior within the cluster. As scientists continue to explore these questions using telescopes and simulations, they inch closer to unraveling the mysteries of galaxy clusters, providing deeper insights into the universe's formation and evolution. Understanding the structure of the universe is crucial for unlocking answers to many larger cosmological questions. Imagine the universe as a vast web, where each strand represents galaxies and clusters of galaxies, interconnected and guiding the flow of cosmic matter and energy. By studying how this web is woven together, scientists can uncover the underlying rules that govern the cosmos. One significant question revolves around the origins of the universe. The way galaxies are distributed gives clues about how the universe began to expand after the Big Bang, shedding light on fundamental processes that shaped our existence. By analyzing the patterns in cosmic structures, researchers can trace back in time and explore how the universe evolved over billions of years. This understanding also relates to dark matter and dark energy, two mysterious components that significantly influence the universe's behavior. While dark matter acts like glue, holding galaxies together, dark energy drives the universe's accelerated expansion. By mapping how visible matter interacts with these unseen forces, scientists gain insights into their nature and the overall energy balance of the cosmos. Furthermore, comprehending the universe's structure aids in refining models of cosmic evolution. These models help predict the universe's future, offering a glimpse into its fate. Will it continue expanding indefinitely, or will gravitational forces eventually lead to a collapse? Each answer guides our understanding of the cosmic timeline, illuminating the past, present, and potential futures. In short, the universe's structure is like a cosmic map, guiding scientists on a journey of discovery. By piecing together its complexities, they not only answer immediate questions about its formation and evolution, but also address profound inquiries about our place within this vast, ever-changing cosmos. Scientists define time in the context of the universe as a measure of change and the progression of events. To grasp this concept, think of time as a continuous river flowing steadily forward, marking the moments that shape the cosmos. This river encompasses everything from the tiniest particles to the vast movements of galaxies. In a broader sense, time is not merely a ticking clock. Instead, it relates to the way objects interact in space. For instance, when we observe a star exploding in a supernova, the event's timing offers insights into the life cycle of that star and the energy expelled into the universe. Time helps us understand evolution, whether it's the formation of planets or the orbit of satellites. In the realm of physics, Albert Einstein revolutionized our understanding of time by linking it with space, a concept known as spacetime. He suggested that time can stretch or contract depending on the strength of gravity and the speed at which an object moves. Essentially, when traveling close to the speed of light, time behaves differently than it does at rest. This blending of time with the fabric of space demonstrates that time is not a fixed entity. Rather, it's intertwined with the universe's dynamics and can be influenced by various factors. Thus, for scientists, time serves as a critical framework for exploring and explaining the universe's behavior and changes, allowing them to decode the mysteries of existence and the unfolding story of the cosmos. The idea that time might be an illusion or does not follow a simple linear path has intrigued scientists and philosophers for many years. One prominent theory comes from the realm of physics, particularly within the framework of relativity. According to Albert Einstein's theories, time and space are intertwined in what is called spacetime. This means that the passage of time can vary depending on speed and gravity. For example, an object moving very fast or in a strong gravitational field experiences time differently than something at rest or in a weak gravitational field. This challenges our everyday understanding of time as a constant experience. Another compelling perspective comes from quantum mechanics, where the behavior of particles at very small scales does not always conform to the straightforward flow of time. In some interpretations, events can appear to happen out of sequence, suggesting that the timeline of reality is much more complex than we perceive. Additionally, The philosophical argument known as eternalism posits that past, present, and future are equally real. In this view, time is not a moving line from the past to the present and into the future, but rather a vast landscape where all points exist simultaneously. This viewpoint radically shifts how we consider events, suggesting that experiences are merely our perceived snapshots of a more tangled framework. All these theories paint a picture of time that is far more intricate than a simple journey from one moment to the next, inviting us to rethink how we understand our world and our existence within it. The idea of time travel captivates our imaginations, yet its roots lie in the serious study of modern physics. At the core of this concept is Einstein's theory of relativity, which describes how time is not a constant as we often perceive it, but rather bends and stretches based on speed and gravity. For example, astronauts on a high-speed journey through space or at significant altitudes experience time differently than people on Earth. Their clocks tick slightly slower, a phenomenon called time dilation. Moreover, the notion of traveling back in time stirs even deeper discussions. Some scientists consider hypothetical scenarios where time loops could exist, much like the idea of a wormhole that connects different points in space and time. If one could enter such a tunnel, it might theoretically allow a person to jump to an earlier moment in their life. However, these ideas raise complex questions. What happens if someone were to change something significant in the past? This is known as the grandfather paradox, leading to intriguing debates about causality and the nature of time itself. In addition to relativity, quantum mechanics introduces another layer of complexity. Some interpretations suggest that multiple realities or timelines could exist simultaneously. This notion might hint at the possibility of altered pasts existing in parallel dimensions, allowing for a different kind of time travel without creating contradictions. While time travel remains speculative and challenged by our current scientific understanding, it pushes the boundaries of physics, encouraging deeper exploration of the universe's mysteries. As scientists continue to study the nature of time, space, and their interconnection, the quest for understanding time travel remains an exciting frontier in modern physics. Time is a fundamental aspect of the universe that helps us make sense of how things operate under the laws of physics. It's like a backdrop against which all events unfold. In our everyday lives, we perceive time as a linear progression, from the past to the present and into the future. This understanding also guides scientists in exploring everything from the movement of planets to the behavior of tiny particles. In physics, time is often used to measure the intervals between events. For example, when we describe how fast something is moving, we relate distance to time. If a car travels a specific distance and we know how long it took, we can calculate its speed. This relationship is crucial because it helps bridge the gap between motion and change. Additionally, time is essential in the theory of relativity, which reshapes our understanding of space, time, and gravity. According to this theory, time is not a separate entity, but rather intertwined with space to create what we call space-time. In simple terms, the effects of gravity can alter the flow of time. Near a massive object like a planet or star, time can slow down compared to a place with less gravitational pull. This means that two observers, one close to a heavy mass and another far away, will experience time differently. Moreover, in the realm of quantum physics, time plays a unique role. Many processes occur at extremely small scales, and the behavior of particles can sometimes seem random and unpredictable. The way these particles interact over time helps scientists understand the underlying rules that govern their behavior. Ultimately, time is not just a measure, it shapes the way we understand and interpret the physical world. From the ticking clock of our daily lives to the vastness of cosmic events, time is woven into the very fabric of reality, guiding the motions and interactions of everything around us. Recent advancements in physics have opened up new avenues of thought regarding time, challenging our classical understanding of it as a simple linear progression from past to future. Traditionally, we see time as a constant, something that ticks away uniformly like a clock. However, new theories suggest that time might not operate in such a straightforward manner. One of the most intriguing concepts has emerged from studies on quantum mechanics. At the smallest scales, particles behave in ways that defy our conventional ideas about cause and effect, suggesting that the sequence of events can exist in a superposition where multiple outcomes happen simultaneously. This introduces the idea that time may not be a fixed path, but rather a more flexible and interconnected experience. Furthermore, the theory of relativity, put forth by Albert Einstein, gives us a different perspective on how time can change depending on speed and gravity. Time can actually run faster or slower depending on how close you are to a massive object, or how fast you are moving relative to another observer. This means that time is not just about the ticking of a clock, it is influenced by the fabric of space itself. Researchers are also exploring the possibility of time being intertwined with the dimensions of space, leading to the notion of time as part of a larger, more intricate structure. The idea that space and time are interwoven reveals that our straightforward comprehension of time may need a significant update as we delve deeper into the universe's fabric. These advancements are pushing scientists to reconsider fundamental questions. Is time an illusion? Can it be reversed? What happens to time in extreme conditions like near black holes? Each new exploration not only expands our understanding of the universe, but also invites us to rethink our place within it, alongside the very nature of reality itself. Dark flow is a fascinating phenomenon in cosmology that suggests the existence of a mysterious influence on the motion of galaxy clusters. To understand it, imagine the universe structured like a vast, expanding ocean where galaxies float like boats. Most galaxies move with the general flow determined by the expansion of the universe. However, dark flow indicates that some galaxy clusters seem to be moving in a specific direction, as if being pulled by an unseen force beyond the ordinary gravity we understand. This strange behavior was first detected through observations made with specific instruments that measure the cosmic microwave background radiation, which is the faint glow left over from the Big Bang. By analyzing tiny temperature variations in this ancient radiation, scientists noted that certain galaxy clusters appeared to be moving toward a particular area of the sky, located in the direction of the constellations Centaurus and Hydra. This motion seemed to defy the gravitational influences of known structures in the universe and hinted at the possibility of some vast and distant entity affecting their movement. The implications of dark flow lead to many intriguing questions. It suggests that there may be regions of mass we cannot see, perhaps due to the presence of structures beyond our observable universe. Understanding dark flow could unlock new insights into the nature of the cosmos, shedding light on forces and elements we have yet to fully explain. Dark flow is a fascinating concept that suggests some regions of the universe are moving in a specific direction, influenced by forces beyond what we can currently see or understand. The evidence supporting the idea of dark flow primarily comes from observations of galaxy clusters and the cosmic microwave background radiation, often referred to as the afterglow of the Big Bang. Researchers have studied the movement of galaxy clusters, which are large groups of galaxies held together by gravity. By measuring their motions, scientists noticed that some of these clusters appear to be moving in a consistent direction, as if being pulled by an unseen force. This is particularly interesting when you consider that many galaxies are distributed fairly evenly across the universe. The fact that some are all moving toward the same area could suggest an influence that aligns more with the scale of the universe itself. In addition, when scientists studied the cosmic microwave background, they found slight variations in temperature across the sky. These variations hint at the early universe's density fluctuations, but some researchers also see patterns that suggest a larger structure may be affecting these measurements. This could indicate that large masses, perhaps outside our observable universe, are exerting influence on everything within it, contributing to the phenomenon of dark flow. While these observations are intriguing, they do not provide a complete picture. Dark flow remains a topic of debate among scientists. Some argue that the observed flow might result from local gravitational effects or other known cosmic structures. Continued research is essential for confirming the existence of dark flow and understanding any implications it may have for our knowledge of the universe. For now, it stands as a captivating mystery in the vast expanse of space, urging scientists to delve deeper into the fabric of cosmic existence. Dark flow is a fascinating phenomenon that reveals more about the universe's expansion and the motion of galaxies. Imagine the universe as a vast ocean where galaxies drift like boats. While these boats generally move according to the expansion of the universe, dark flow suggests that some are being pulled by unseen forces, rather like currents in the water. Observations of galaxy clusters indicate that they appear to move in a specific direction, pointing to a coherent flow that does not align with the standard model of cosmic expansion. This movement hints at the presence of mass that is not directly observable, perhaps related to structures beyond the observable universe. This uncharted territory raises intriguing questions. If dark flow exists, it implies that there are larger cosmic structures influencing our local group of galaxies, creating a sort of cosmic wind. Understanding this flow challenges scientists to rethink how these massive gravitational influences operate on a grand scale. The concept of dark flow also suggests that our universe may be part of a larger multiverse, with other regions of space that are also interacting with us. Dark flow offers a glimpse into the hidden forces acting across greater distances than we can currently see. It motivates researchers to refine their understanding of cosmic movements and the architecture of the universe. As scientists continue to study these phenomena, dark flow may help illuminate the mysteries of gravity and the large-scale structure of galaxies, drastically changing our view of the cosmos. Dark flow refers to a mysterious phenomenon observed in the large-scale motion of galaxy clusters, suggesting they are moving in a particular direction at unexpected speeds. Scientists have developed several hypotheses to explain this phenomenon, each trying to unravel the deeper mysteries of our universe. One major hypothesis is that dark flow arises from gravitational influences beyond our observable universe. Imagine the universe as an ocean of galaxies, but beyond the horizon there could be vast structures that we cannot see. These unseen regions might exert a pull on the galaxy clusters, causing them to move in a specific direction. This idea aligns with the notion that our universe is not neatly contained, but rather exists within a much larger and possibly more complex cosmic structure. Another possibility suggests the existence of a significant mass concentration, like a supercluster or a series of massive galaxy clusters that act like a gravitational anchor. This massive collective could be influencing the motion of other galaxy clusters, pulling them along with the flow. Such massive structures could serve as the source of the dark aspect of dark flow, suggesting unseen forces are in play in the cosmos. Some scientists also consider the role of dark energy, a mysterious force believed to be driving the accelerated expansion of the universe. While dark energy typically causes galaxies to move apart, it's conceivable that it could also influence the motion of galaxy clusters in unexpected ways. Understanding the interplay of dark energy and dark flow remains a fascinating area of research. As researchers gather more data and refine their observations, they hope to shed light on this cosmic drift, revealing the underlying mechanics of the universe and perhaps uncovering new realms of physics that lie just beyond our current understanding. Each hypothesis provides a glimpse into the complexities of the cosmos, highlighting the ongoing journey to grasp the profound nature of dark flow and its implications for our understanding of the universe. The dark flow mystery intrigues scientists as it suggests that our universe may not be quite as uniform and isotropic as we once thought. Dark flow refers to the strange, coordinated movement of galaxy clusters that seem to drift in a specific direction, hinting at some unseen force or structure beyond our observable universe. This could mean that there are larger structures, possibly from a past universe or regions beyond what we can currently detect, influencing these movements. If researchers were to resolve the mystery of dark flow definitively, it could lead to a significant shift in our cosmological theories. For instance, it might challenge the widely accepted model that the universe is homogeneous, meaning similar in all directions when viewed on a large scale. Instead, evidence of dark flow could support the idea that there are vast cosmic structures and phenomena influencing galaxies over immense distances. Additionally, new insights into dark flow could lead to re-evaluating the nature of dark energy, the mysterious force thought to be causing the accelerated expansion of the universe. If these galaxy clusters are being pulled by something beyond our observable universe, it raises questions about the dynamic nature of space itself. Such discoveries would not only impact theoretical physics, but might also redefine our understanding of the universe's history and evolution. We could begin to perceive galaxies not as isolated entities, but as part of a much greater cosmic web, interconnected in ways we are just beginning to understand. Ultimately, resolving the dark flow mystery could invite new questions and foster innovative theories, urging us to rethink our place in the vast and complex universe. For life to exist beyond Earth, certain conditions are generally considered essential. These conditions center around the presence of elements, energy sources, and stable environments. The first crucial element is water. Life as we know it relies heavily on water, which acts as a solvent that facilitates chemical reactions necessary for biological processes. Scientists often look for planets or moons where liquid water might exist. Another fundamental requirement is an energy source. Life needs energy to grow, reproduce, and maintain itself. On Earth, the most common energy source is sunlight, which drives photosynthesis in plants. However, other forms of energy could support life, such as the heat produced by geological activity or even chemical energy from minerals. Additionally, the right chemical elements must be present, primarily carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These elements combine to form the building blocks of life, such as proteins and nucleic acids, which are vital for cellular function and reproduction. Stable environmental conditions are also critical. This includes a suitable temperature range and atmospheric conditions that can protect life from harmful radiation and provide necessary gases for respiration and photosynthesis. Too much temperature fluctuation can pose risks to any potential living organisms. Finally, a planet or moon needs to have a long enough duration for life to evolve. This means having a stable orbit and conditions that allow for a steady climate over millions of years, providing the necessary time for complex life forms to develop. While the specific conditions may vary, a combination of liquid water, a reliable energy source, essential chemical elements, stable environmental conditions, and sufficient time appear to be fundamental for life to emerge elsewhere in the universe. Scientists continue to explore the cosmos, searching for places where these conditions might align, signaling the potential presence of life beyond our home planet. The search for life beyond Earth has become one of the most exciting areas of modern science. Over the years, scientists have identified several key factors that contribute to a planet's potential to support life. First, the presence of liquid water is crucial. Water is a vital ingredient for life as we know it, and it has been found on moons like Europa and Enceladus, as well as on Mars. These discoveries suggest that conditions might be suitable for microbial life. Next, scientists examine the types of atmospheres present on other planets. An atmosphere can protect life from harmful space radiation and temperature extremes. For example, planets in a star's habitable zone, where conditions could allow for stable liquid water, are of particular interest. This zone is often referred to as the Goldilocks zone because it is not too hot and not too cold. In addition to water and atmosphere, the chemical composition of a planet is important. Elements like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur are essential building blocks for life. When astronomers study the atmospheres of exoplanets, they look for these elements, searching for signs of organic molecules that could indicate biological processes. The exciting news is that scientists have discovered thousands of exoplanets, planets outside our solar system, some of which share characteristics similar to those of Earth. These findings raise the possibility of diverse environments that could harbor life, although any such life might differ greatly from what we understand. Moreover, the more we explore our own solar system, the more we learn about the potential for life beyond Earth. For example, the discovery of extremophiles, organisms that thrive in extreme environments on Earth, challenges our assumptions about where life can exist. If life can flourish in harsh conditions on our planet, similar life forms might be thriving in the icy plumes of distant moons or in the depths of other planets' oceans. Despite these exciting discoveries, we have yet to find definitive evidence of extraterrestrial life. Ongoing missions, such as those on Mars, the study of the atmospheres of distant planets, and the exploration of icy moons continue to drive the search. Each mission enhances our understanding and brings us closer to unraveling the mystery of whether we share the universe with other living beings. The journey is not just about finding life, it is about understanding our place in the cosmos and the vast potential of life in different forms. Scientists are on a constant quest to find extraterrestrial life, embracing a variety of strategies and technologies to explore this vast mystery. The search often begins with understanding the conditions that can support life. On Earth, life thrives in environments once thought inhospitable, such as deep-sea vents and icy landscapes. This insight leads researchers to focus on celestial bodies that might harbor similar conditions. One significant approach involves studying planets and moons in our solar system. For example, missions to Mars look for evidence of water and organic molecules, as these are crucial components for life. Instruments on rovers can analyze soil and rock samples, detecting chemical signs that suggest biological activity, past or present. Beyond Mars, Europa, one of Jupiter's moons, is intriguing due to its icy surface that conceals a liquid ocean beneath, providing a potential habitat for life. Astronomers also turn their gaze toward distant stars and their planets, known as exoplanets. They use powerful telescopes to observe how these planets move in front of their stars, causing slight dimming of light. This technique, called the transit method, allows scientists to determine the size and orbit of the planet, helping to identify those located in the habitable zone, where conditions might be just right for liquid water to exist. Moreover, researchers are keen on analyzing the atmospheres of these exoplanets for specific gases, particularly those associated with biological processes like oxygen and methane. The simultaneous presence of these gases might indicate life forms, as they often react with one another and would not likely coexist in large quantities unless replenished by living organisms. Another exciting method involves the search for signals from advanced civilizations beyond Earth. Using radio telescopes, scientists listen for patterns in the cosmos, hoping to detect deliberate communication. These signals would provide compelling proof of intelligent life. Lastly, astrobiology, a field dedicated to understanding life's potential in the universe, combines knowledge from various disciplines, biology, chemistry, and planetary science, to create models that predict where and how life might arise and develop in environments outside our own. Through these diverse techniques, scientists constantly expand their understanding of what life might look like beyond our planet and where it might be found amidst the stars. Their search is not just about finding life. It's about uncovering the truth of our universe and our place within it. The Fermi paradox presents a fascinating puzzle about our universe. Named after the physicist Enrico Fermi, the paradox arises from the contrast between the high probability of extraterrestrial civilizations existing and the stark lack of evidence for their presence. Given the vast number of stars and planets in our galaxy alone, one would expect that intelligent life should be common. So, where is everyone? Several explanations have been proposed to unravel this mystery. One possibility is that intelligent life is indeed rare. Perhaps the conditions needed for life, and particularly for intelligent life, are so unique that we are privileged observers of a one-off event in cosmic history. In contrast, simple life forms might be abundant, but they don't evolve into complex civilizations. Another theory suggests that technology advanced enough for interstellar communication or travel might not last long. Civilizations could rise and fall, extinguishing themselves before they get a chance to reach out to the stars. This could mean we are living in a brief window of time where civilization has the capability to explore and communicate, but the window is so narrow that we miss each other. Alternatively, it's possible that intelligent species do exist, but they are choosing not to contact us. This could be a deliberate choice, perhaps guided by a prime directive, similar to what we see in fictional contexts, a rule against interfering with developing civilizations. Or they may be using communication methods beyond our current understanding, rendering their signals undetectable by our technology. Another intriguing idea is the Great Filter, suggesting there's a challenging step in the evolutionary progression that most life fails to overcome. This filter could be behind us, implying that intelligent life surviving long enough to colonize the galaxy is exceedingly rare. Or it may lie ahead of us, warning that advanced civilizations tend to self-destruct before achieving interstellar travel. Finally, some hope remains that intelligent civilizations simply do not want to be found, exploring the universe quietly or living in technologically advanced hidden societies. Whatever the truth may be, the Fermi paradox continues to compel scientists and thinkers alike to explore the possibilities of life beyond our own planet. inviting us to wonder about our place in the cosmos. Discovering extraterrestrial life would profoundly change human society in ways we can only begin to imagine. Initially, it would spark a mix of excitement, curiosity, and perhaps fear. This groundbreaking finding would challenge our understanding of what it means to be human. The existence of life beyond Earth would raise big questions about our place in the universe and our connection to other life forms. Socially, it could unite humanity in shared wonder and purpose. The thought that we are not alone might foster a sense of global community, as people from diverse backgrounds come together to learn and explore this new reality. National borders could seem less significant in the face of a shared identity as Earthlings. Culturally, art, literature, and philosophy would likely flourish as we seek to express and comprehend this discovery. New narratives would emerge, exploring the implications of coexistence with other civilizations. The impact on religion could also be profound, encouraging new interpretations and discussions about creation and life itself. Technologically, the discovery might drive innovation and collaboration. If communication with extraterrestrial beings were possible, it could lead to advancements in science, medicine, and technology as we learn from their knowledge. This quest could inspire generations of scientists and explorers eager to uncover the mysteries of the universe. However, this monumental discovery would also come with challenges. The reality of extraterrestrial life could instigate fear, mistrust, and conflict, prompting questions about our defenses and the potential for interactions that could alter our society drastically. Ethical considerations would arise about how we approach these beings and how we might share our planet and resources. The discovery of extraterrestrial life would likely act as a catalyst for change, influencing our social structures, cultural identities, and scientific pursuits, all while posing complex emotional and ethical dilemmas. It would open a new chapter in human history, inviting us to rethink everything we know about life in the universe. Gravity is a fundamental force that plays a crucial role in shaping the universe. It is the invisible glue that holds everything together, influencing the movement of objects, the formation of structures, and even the life cycles of stars and galaxies. To understand gravity's impact, think of it as a tapestry woven with countless threads. All the mass in the universe, from the smallest particles to the largest galaxies, pulls on these threads, creating a complex structure. The most noticeable effect of gravity is its role in the formation of celestial bodies. Planets, stars, and galaxies all arise from massive clouds of gas and dust in space. Over time, gravity causes these masses to clump together. As material gathers, the gravitational pull becomes stronger, attracting even more matter and creating larger structures. This process is akin to a snowball rolling down a hill, collecting more snow as it moves. Once these structures are formed, gravity continues to dictate their behavior. It keeps planets in orbit around stars and stars in orbit within galaxies. Without gravity, celestial bodies would drift apart into empty space, disrupting the harmony of the universe. Gravity also affects the very fabric of space and time itself. Near incredibly dense objects like black holes or neutron stars, the warping of space can be so extreme that it alters how we perceive distances and time. Furthermore, on a grander scale, gravity contributes to the cosmic web, a vast network of galactic clusters and filaments interconnected by gravity. It determines how these groups of galaxies gather, collide, and eventually unite into superclusters. As the universe expands, gravity plays a persistent role, fighting against this expansion by pulling matter together. In short, gravity is not merely a force, it is a shaper of reality. It molds the universe into the intricate cosmic structure we observe, from swirling galaxies to our very own solar system. Understanding gravity helps us appreciate the delicate balance that governs the movements of all celestial objects and the universe as we know it. Gravity is one of the fundamental forces in the universe, yet it holds several mysteries that continue to puzzle scientists. One of the most significant questions is how gravity fits into the broader framework of physics. While we understand gravity well in terms of its effects on large objects like planets, stars, and galaxies, it's challenging to reconcile it with quantum mechanics, which explains the behavior of very small particles. Essentially, we lack a complete theory that combines the vast scale of gravity with the tiny scale of the quantum world. Another mystery revolves around the nature of dark matter. Observations show that the universe contains much more mass than we can see. This unseen mass, which doesn't emit light or energy, is believed to be responsible for the gravitational effects we observe in galaxies. Scientists continue to debate whether dark matter is composed of new, yet-to-be-discovered particles, or if there are modifications needed in our understanding of gravity itself. Furthermore, there's the enigma of dark energy. This mysterious force appears to be driving the acceleration of the universe's expansion, but its origin and nature remain elusive. Does it represent a new form of energy, or could our understanding of gravity need to be adjusted on cosmic scales? Lastly, we still do not fully comprehend how gravity operates at absolute extremes, such as near a black hole. The behavior of gravity in these conditions challenges our current theories and suggests that there might be undiscovered rules governing spacetime. These unresolved questions not only highlight the limits of our current knowledge, but also open the door for potentially groundbreaking discoveries in the future. As we explore this fundamental force more deeply, we may uncover profound truths about the universe itself. Gravity and relativity intertwine in a fascinating and essential way, especially when we consider the vastness of the universe. At its core, gravity is the force that pulls objects together. This force is felt by everything with mass, from small rocks to massive stars. Relativity, particularly Einstein's theory of general relativity, offers a deeper understanding of how gravity operates. In simple terms, general relativity describes gravity not as a traditional force, but as a curvature of space and time. Imagine placing a heavy ball on a trampoline. The ball creates a dip, causing smaller balls nearby to roll toward it. In this analogy, the trampoline represents the fabric of space-time. Massive objects like planets, stars, and galaxies warp space-time around them, affecting the paths of other objects nearby. On a cosmic scale, this means that the presence of large bodies affects not only their immediate surroundings, but also contributes to the dynamics of entire galaxies and clusters. For instance, when light from a distant star travels to us, it passes near a massive galaxy. The warped space-time around that galaxy can bend the path of the light, making the star appear in a slightly different position than it truly is. This effect is known as gravitational lensing, and it allows astronomers to study distant galaxies otherwise hidden from view. Moreover, as objects with mass move through this curved spacetime, they experience changes in time, an effect known as time dilation. This means that time can flow more slowly in stronger gravitational fields compared to weaker ones. So on a cosmic journey, someone near a massive object would age more slowly than someone further away, which adds another layer to our understanding of the universe. Understanding how gravity and relativity interact helps scientists make sense of complex phenomena, such as black holes, which are regions of space where gravity is so strong that nothing, not even light, can escape. Thus, the relationship between gravity and relativity is a cornerstone for grasping the mysteries of the cosmos, revealing how everything from the smallest particles to the largest galaxies communicates through the universal language of space-time. Gravitational waves are ripples in the fabric of space and time, created when massive objects accelerate, such as when two black holes collide or when neutron stars orbit each other. Imagine throwing a stone into a calm pond. The ripples spread outward from the point of impact, disturbing the surface of the water. Similarly, when massive celestial bodies interact, they generate waves that travel across the universe at the speed of light, distorting space itself as they pass through. These waves were first predicted by Albert Einstein over a century ago as part of his theory of general relativity, but it wasn't until recently that we detected them directly. The detection of gravitational waves is like opening a new window to the universe, allowing scientists to observe phenomena that were previously invisible. Traditional astronomy relies on light, whether from stars, galaxies, or cosmic events, to gather information. Gravitational waves provide a different perspective, revealing the dynamic, violent processes occurring in the cosmos. The effect of gravitational waves on our understanding of the universe is profound. They enable us to study events that are hard to capture in light, like the mergers of black holes or neutron stars. This new method of observation has already led to insights about the rate of expansion of the universe and the nature of stellar evolution. Gravitational waves enrich our cosmic narrative, offering clues about the very foundations of space and time and deepening our insight into the workings of the universe. Understanding gravity is one of the biggest puzzles in physics. If we can fully unravel its mysteries, the potential advancements in science could be groundbreaking. For starters, a deeper grasp of gravity could lead to significant strides in our understanding of the universe. Right now, we know gravity governs everything from the fall of an apple to the orbits of planets and galaxies. But there are still many unanswered questions, especially regarding how gravity interacts with other fundamental forces like electromagnetism. One major advancement could be the development of new technologies. For example, if we were able to manipulate gravitational forces, it might pave the way for revolutionary transportation systems. Imagine spacecraft that can harness gravity to travel vast distances at unprecedented speeds. This could allow us to reach distant planets or even other stars in a fraction of the time it currently takes. Additionally, understanding gravity could enhance our approaches to energy production. Gravity is a powerful force, and unlocking its full potential might inspire new forms of energy generation, perhaps creating more sustainable and efficient ways to power our world. On a more profound level, unraveling gravity might also lead to a new understanding of space-time, the fabric that combines the three dimensions of space with the dimension of time. This could inform theories about black holes, dark matter, and dark energy, phenomena that currently elude complete explanation. Furthermore, there could be implications for our understanding of the beginning of the universe. More knowledge about gravity might help us understand the conditions that existed just after the Big Bang, potentially leading us to insights about the very origin of our existence, pushing the boundaries of what we know about physics and cosmology. Deciphering the intricacies of gravity could lead to breakthroughs not just in understanding the universe, but also in how we interact with it, transforming technology, energy systems, and our grasp of fundamental physics. The possibilities are as vast as the cosmos itself. Light travels across the universe as a form of energy that moves in waves. To understand this journey, think about light as a stream of tiny particles called photons. When these particles are produced, such as in a star, they set off traveling at incredible speeds, roughly as fast as anything can go in our universe. As light begins its journey, it moves through the emptiness of space, covering distances that are hard to imagine. Unlike sound, which needs air or another medium to move, light can travel through the vacuum of space. This ability allows it to traverse the vast emptiness between stars, galaxies, and other celestial objects without interruption. However, light doesn't always have a smooth journey. It can be affected by various factors along the way. For instance, if it passes near a massive object, such as a star or a black hole, the intense gravity of that object can bend the light's path, a phenomenon known as gravitational lensing. This bending can cause the light from distant stars to appear distorted or even multiply into multiple images. Another interesting aspect of light is its interaction with dust and gas in space, particularly in areas where stars are being born. As light travels through these regions, it can be scattered or absorbed, which can change its color. This is why we might see certain nebulae glowing in beautiful shades of red, blue, and green. The light emitted from nearby stars is filtered through the fog of interstellar dust. Ultimately, light from a star can continue its journey for millions or even billions of years before reaching our eyes, allowing us to gaze back in time, observing not just the stars, but the very history of the universe itself. Each flicker we see in the night sky tells the story of a journey vast and ancient, connecting us to the cosmos in ways that are both profound and deeply fascinating. Light from distant celestial objects is like a treasure trove of information waiting to be uncovered. When we observe light, we are not just seeing the object itself, we are gaining insights into its composition, temperature, distance, speed, and even its motion through space. The different colors within the light spectrum can reveal a lot about what the object is made of. Each element emits or absorbs light at specific wavelengths, akin to a unique fingerprint. By analyzing the color patterns, scientists can identify the elements present in that celestial body. Furthermore, light can tell us about temperature. Hotter objects emit light of shorter wavelengths, which appear bluish, while cooler objects emit longer wavelengths, making them look reddish. This principle helps astronomers determine the temperatures of stars and other celestial bodies. Distance is also conveyed through light. As light travels across the vast expanse of space, it can become stretched if the object is moving away from us, causing a phenomenon known as redshift. By measuring how much the light is stretched, astronomers can infer how fast an object is moving and how far away it is. All this information is captured in the light that reaches Earth, allowing us to piece together a comprehensive picture of the universe even from incredible distances. When we look at the stars far away, we are essentially looking back in time, as the light takes years to travel to us. Each ray of light is not just a means of seeing, it is a messenger, delivering the secrets of the cosmos from the past. Redshift and blueshift are crucial concepts that help us understand the universe's expansion and the movement of celestial objects. These shifts occur due to the Doppler effect, which explains how the wavelength of light changes depending on the relative motion between a source and an observer. When an object in space moves away from us, the light it emits is stretched, causing the wavelengths to shift toward the red part of the spectrum. This is known as redshift. Imagine playing a sound as a vehicle drives away from you. The pitch drops as it moves farther away. Similarly, redshift reveals that many galaxies are moving away from us, suggesting that the universe is expanding. This discovery has been fundamental in shaping our understanding of how the cosmos has changed over billions of years. On the other hand, when a celestial object moves closer, its light is compressed, resulting in a shift toward the blue part of the spectrum, termed blueshift. This is less common because most galaxies are receding, but it can be observed in objects like certain stars that are approaching us. By analyzing these shifts, astronomers can determine not only the direction and speed of objects in the universe, but can also infer their distance. The greater the redshift, the faster an object is receding, giving scientists vital information about the rate of cosmic expansion. This interplay of distances and speeds plays a significant role in understanding the fate of the universe, its structure, and how it came to be. Through redshift and blueshift, we have a powerful tool for exploring the vastness of space and unveiling the mysteries of cosmic phenomena. Scientists have developed clever methods to use light in order to measure great distances in space and track the passage of time. Light is incredibly helpful because it travels at a consistent speed through the vacuum of space, making it a reliable tool for understanding the universe. One of the primary methods involves observing a phenomenon known as parallax. When Earth moves in its orbit around the Sun, nearby stars appear to shift against the more distant background of stars. By measuring this tiny movement, scientists can calculate the distance to the star. Imagine holding up your finger in front of your face and closing one eye, then switching to the other eye. Your finger seems to jump position relative to the background, illustrating how we can gauge distance based on angles. Additionally, astronomers use a type of light called standard candles. These are specific stars, such as certain types of supernovae, that have a known brightness. By comparing their known brightness to how bright they appear from Earth, scientists can determine how far away they are. If something looks dimmer, it must be farther away, similar to how distant streetlights appear less bright than those nearby. For measuring time, scientists often refer to the speed of light itself. When we observe distant celestial events like a supernova, we are seeing light that has traveled for years to reach us. The time it takes for light to arrive allows us to determine how long ago that event occurred. For example, if we see light from a star that is millions of years old, it means the explosion happened millions of years ago, showing us a glimpse into the past. By using these principles of light, scientists construct a profound understanding of the vast distances between celestial bodies and how time unfolds across the cosmos. Each observation not only reveals more about our universe, but also connects us through time and space to events happening far beyond our own world. Studying light from the farthest reaches of the universe poses several significant challenges. First and foremost, the vast distance light travels before reaching us means it can take billions of years to arrive, making it like peering into the distant past. This delay can lead to difficulties in interpreting the light we receive, as it undergoes changes and may appear differently than it did when it was first emitted. Another challenge comes from the sheer amount of cosmic material, like gas and dust, that exists in space. This material can absorb or scatter light, making objects dimmer or altering their colors. When astronomers observe these distant sources, they must carefully account for these distortions to understand the true nature of what they are studying. Additionally, the expansion of the universe stretches the light emitted by distant objects, shifting it towards the red end of the spectrum. This phenomenon is known as redshift. As light stretches, it can move out of the range of visible light, making it difficult to detect with standard telescopes. Researchers often use specialized instruments to capture this shifted light, but analyzing the data requires advanced techniques and often complex calculations. Finally, the technological constraints of our instruments can limit the details we gather from these remote areas. Telescopes must be powerful enough to collect faint light, yet they also face challenges such as atmospheric distortion caused by our own planet's air, which can blur the images. To overcome this, scientists often place telescopes in space where there is no atmosphere to interfere, leading to clearer observations. All these factors combined create a complex puzzle for scientists who must be adept at interpreting faint, distorted signals from the cosmos while using advanced technology to uncover the mysteries of our universe's most remote corners. Quantum entanglement is a fascinating phenomenon that occurs in the realm of quantum physics. To understand it, imagine you have two particles that are interconnected, like two dancers moving in perfect unison. When one dancer changes their position, the other dancer instantly adjusts their movement, no matter how far apart they are. This instant connection between the two particles is what we call entanglement. In classical physics, which governs our everyday experiences, objects are independent unless they interact. For example, if you throw a ball, its trajectory depends only on the forces acting on it at that moment. However, in the world of entanglement, the state of one particle can influence another particle instantly, even if they are light years apart. This idea challenges our traditional understanding of space and time. One of the most striking aspects of entanglement is that it seems to defy the principle that information cannot travel faster than the speed of light. When entangled particles are measured, the results are correlated in ways that classical physics cannot explain. This means that changing the state of one entangled particle adjusts the state of its partner right away, no matter the distance separating them. It raises profound questions about what we know of reality and how we perceive the universe. Entanglement suggests that at a fundamental level, the universe is much more interconnected than we once thought. It invites us to reconsider the fundamental influences of energy and existence, pushing the boundaries of both physics and philosophy as we explore the true nature of reality. Quantum entanglement is one of the most intriguing phenomena in the realm of physics, challenging our conventional understanding of space and time. To grasp its implications, picture two particles that become linked in such a way that the state of one instantly influences the state of the other, no matter how far apart they are. This connection raises profound questions about the nature of reality and the fabric of the universe. When these particles are entangled, a measurement performed on one immediately provides information about the other. This happens regardless of the distance separating them, suggesting that some form of communication or connection transcends our typical notions of space. Such behavior seems to imply that space, as we know it, a medium through which information travels, might not be as fundamental as we once thought. Furthermore, this phenomenon prompts us to reconsider our understanding of time as well. Since the connection between entangled particles appears instantaneous, it challenges the idea of cause and effect occurring in a linear sequence. What if information can correlate across vast distances without regard to the time it takes to travel in our familiar three-dimensional space? Scientists are still wrestling with these ideas as they delve deeper into the implications of entanglement for theories of the universe. This leap in thinking encourages researchers to explore how entanglement might reveal hidden dimensions or unknown aspects of the cosmos. If particles can be connected in such a way that defies conventional limits of locality and separateness, could it mean that space itself is an emergent property, originating from deeper, more intricate relationships between fundamental particles? Quantum entanglement not only alters our understanding of particle interactions, but also pushes the boundaries of how we perceive space and time. It invites us to rethink the very structure of reality, asking what lies beyond the ultimate limits we once thought were insurmountable. Quantum entanglement is a fascinating phenomenon where two or more particles become linked in such a way that the state of one instantly influences the state of another, regardless of the distance separating them. To explore this concept at cosmological scales, essentially the vast expanses of the universe, scientists have devised several innovative experiments. One significant experiment involved utilizing pairs of photons, which are particles of light, generated by a source on Earth. These photons were entangled, meaning that their properties were interconnected. In the experiment, one photon was sent toward a distant location while the other stayed behind. To test entanglement, researchers measured the properties of the traveling photon, then compared those results with the measurements taken on the second photon. Remarkably, the outcome of the measurement on one photon appeared to influence the other instantaneously, regardless of whether they were separated by large distances. Another intriguing approach involved observing pairs of photons that originate from cosmic events, such as the interactions of radiation emitted by distant galaxies. Here, researchers used telescopes to capture the light coming from these cosmic sources, looking for patterns indicative of entanglement. Such experiments allow scientists to assess whether the entangled particles behave as theorized, even across the great void of space. Furthermore, experiments have extended to testing the foundations of quantum theory itself. By examining how entangled particles behave when subjected to different conditions, researchers aim to determine if local hidden variables could explain their correlations, or if the results confirm the predictions of quantum mechanics across cosmic scales. By conducting these experiments, researchers are not just testing quantum physics, they are gaining insights into the fundamental nature of the universe. The implications of successfully observing quantum entanglement in these contexts are profound, potentially reshaping our understanding of reality at both the smallest and largest scales. Events that occur billions of light years away could, according to quantum entanglement, still communicate information instantaneously. The quest for knowledge in this area is ongoing, propelling us further into the mysteries that lie at the intersection of quantum mechanics and the cosmos. Quantum entanglement is a fascinating phenomenon where two particles become linked in such a way that the state of one instantly influences the state of the other, no matter how far apart they are. This connection challenges our traditional understanding of space and time. Imagine two dancers performing a perfect routine together. Even if one dancer is across the world, the moment one moves, the other responds as if they were in perfect sync. This strange behavior raises significant questions about the fundamental nature of the universe. Current theories suggest that everything in the universe is interconnected in ways we are just beginning to understand. Traditional physics views particles as individual entities, but entanglement hints at a deeper web of connections, as if the universe itself is a vast tapestry where every thread is intricately woven together. Moreover, entanglement has implications for our understanding of information and reality. When particles are entangled, the information about their states is shared instantaneously, which seems to defy the limitations set by the speed of light. This has led scientists to propose new theories that could redefine how we think about causality, suggesting that events in the universe may not always be determined by local interactions. As researchers explore the implications of quantum entanglement, they are considering its role in everything from the fabric of space-time to the workings of black holes. Some theories even posit that entangled particles could help us unravel the mysteries of dark matter and dark energy, which make up a vast majority of our universe but remain largely elusive. In this way, quantum entanglement not only challenges our current understanding of physics, but also opens doors to new theories that could reshape our view of the cosmos. Quantum entanglement is a fascinating phenomenon where particles become interlinked, such that the state of one instantaneously affects the state of another, no matter how far apart they are. This peculiar connection hints at profound implications for our understanding of the cosmos. One of the most exciting areas of exploration is how quantum entanglement might reshape our view of the universe's structure and evolution. As scientists delve deeper into quantum mechanics, they could uncover new ways to observe and understand cosmic phenomena. For instance, if entangled particles can share information faster than light, as some theories suggest, this might offer insights into how distant galaxies influence one another, fundamentally altering our conception of space and time. Additionally, quantum entanglement could play a key role in dark matter studies. Dark matter makes up a significant part of the universe, but it remains elusive. By exploring entangled particles, researchers may identify new interactions that could lead to the discovery of dark matter particles, ultimately revealing the unseen forces that shape our universe. Then there's the potential for advancements in gravitational wave detection. If quantum entanglement can enhance sensitivity in measuring these ripples in space-time, we could gain a deeper understanding of cosmic events like black hole collisions or supernovae. This could improve our grasp of the universe's most violent and energetic processes. Moreover, the interplay between quantum mechanics and general relativity, two pillars of modern physics, could lead to groundbreaking theories that unify them. By studying entangled particles in gravitational fields, scientists might solve mysteries surrounding the origins of the universe, answering questions about the Big Bang or the nature of black holes. As we unlock the secrets of quantum entanglement, we may find ourselves at the forefront of new discoveries in cosmology, from understanding cosmic connections to unveiling the fabric of reality itself. The future holds the promise of revolutionizing how we perceive the universe and our place within it. The formation and evolution of galaxies are driven by a series of interconnected processes that begin with the universe's very inception. After the Big Bang, which was the event that created the universe, it was filled with hot, dense gas made mostly of hydrogen and helium. As the universe expanded and cooled, tiny fluctuations in density began to form. These areas of slightly higher density acted like seeds for galaxies. Over time, gravity played a crucial role. It pulled in more gas and dust, causing these initial densifications to grow. The collapsing gas began to spin, which is similar to how a figure skater spins faster as they pull their arms in. This spinning motion helped flatten the material into rotating disks, which is a common structure seen in many galaxies today. As galaxies formed, they continued to grow by merging with other smaller galaxies. This process of merging not only added more stars and gas, but also resulted in complex interactions, causing new star formation. Regions within galaxies were often compressed enough by collisions, leading to the birth of new stars at a rapid rate, fueling further evolution. The movement of stars within a galaxy also contributes to its development. Stars orbit around the center, and as they age, they produce new elements through nuclear fusion. When they eventually die, especially in dramatic explosions called supernovae, they spread these elements into the surrounding space. This enriches the interstellar medium, the gas and dust that exists between stars, allowing for the formation of new stars with more complex chemical compositions. Additionally, the role of dark matter cannot be overlooked. Though invisible and detectable only through its gravitational effects, dark matter makes up a significant portion of the universe. It forms a halo around galaxies, influencing their formation, growth, and stability. This mass collection helps keep galaxies intact and guides their interactions with one another. As galaxies evolve, they can change dramatically over billions of years. Some may grow larger, becoming what we call spiral or elliptical shapes, while others can become irregular due to gravitational interactions. The balance between star formation and the removal of gas through processes like supernova explosions or the influence of a supermassive black hole at the galaxy's center also affects how galaxies change over time. Overall, the processes driving galaxy formation and evolution are a dance of gravity, gas dynamics, star birth and death, and the mysterious influence of dark matter, creating the magnificent structures we observe in the universe today. The interactions between galaxies play a crucial role in shaping their development throughout time. Picture galaxies as massive collections of stars, gas, and dust moving through the vastness of space. As they drift, they can get too close to one another, leading to gravitational pulls that can significantly alter their structures. When two galaxies encounter each other, several interesting events can occur. Initially, the gravitational forces start to interact, distorting their shapes. This is similar to how two people trying to walk past each other in a crowded hallway might bump and push. These interactions can trigger the formation of new stars, as clouds of gas and dust are compressed in the gravitational tug-of-war. This star formation can lead to bursts of brightness and new celestial objects emerging from the chaos. In more extreme cases, galaxies can merge, combining their mass and resources. This colossal event can drastically change the characteristics of both galaxies. Imagine pouring two different mixtures into one larger container. The result will be a new and complex blend. The resulting merged galaxy may develop a new shape and structure, often becoming larger and more diverse than either of the original galaxies. Through these interactions, galaxies can also exchange material. This transfer can enrich the galaxies with new stars and elements, leading to further evolution. Additionally, when galaxies collide, they can sometimes trigger new star births, creating dazzling displays of light as fresh stars ignite in the crowded conditions created by the merger. Over billions of years, these interactions influence the overall galaxy population in the universe. They can lead to the formation of galaxy clusters and influence the distribution of matter in space. Understanding these processes helps astronomers decipher the history of galaxies and the dynamic nature of our universe. Each interaction leaves a mark, crafting a story of evolution bound together by the invisible force of gravity. Scientists have uncovered fascinating insights into the life cycle of galaxies, revealing their dynamic and ever-changing nature. A galaxy begins its life as a vast cloud of gas and dust. Over time, gravity pulls these materials together, sparking the birth of stars. This phase can be thought of as the beginning of a galaxy's evolution, where the stars form in clusters, shining brightly and illuminating their surroundings. As these stars live and die, they play a crucial role in shaping the galaxy. Massive stars evolve quickly, exploding in spectacular supernovae at the end of their lives. These events scatter heavy elements throughout the galaxy, enriching the interstellar medium and providing the building blocks for new stars and planets. This recycling process fosters a continuous cycle of birth and death, allowing galaxies to grow more complex as they mature. Interestingly, galaxies are not isolated entities. They often interact and merge with one another. These collisions can trigger a burst of star formation as the gravitational forces compress gas and dust. This phenomenon can lead to the creation of a new, larger galaxy over time, showcasing how galaxies evolve through interactions in the cosmic neighborhood. Eventually, a galaxy may enter a quieter phase where star formation slows down. Older stars dominate the landscape as fewer new stars ignite. This situation can lead to the development of elliptical galaxies, which are no longer producing stars at the same vigorous rate. Their appearance often reflects a smooth, featureless structure compared to the spiral shapes of younger galaxies that continue to actively form stars. Ultimately, the life cycle of a galaxy is a complex and interconnected narrative, driven by the interplay of gravity, stellar evolution, and cosmic collisions. Each stage lays the groundwork for the next, telling a story that spans billions of years and reveals the intricate web of the universe. The study of galactic transformation reveals a great deal about the history of our universe. Galaxies are like time capsules, containing clues about their past and the events that led to their current forms. To understand this, let's consider the life cycle of a galaxy, which can change due to various factors such as collisions with other galaxies, the birth and death of stars, and the inflow or outflow of gas. When galaxies collide, they often merge, creating new structures and sometimes forming even larger galaxies. This helps scientists to understand how galaxies grow over billions of years. By observing these mergers and their outcomes, researchers can piece together a timeline of galactic evolution. For example, if we look at a young galaxy in the early universe, it may appear chaotic and irregular. Over time, as it interacts with other cosmic structures, it may evolve into a more orderly spiral or elliptical shape, similar to what we see in many galaxies today. Furthermore, studying the light emitted by galaxies also gives us insight into their composition. The light reveals the types and ages of stars within, allowing scientists to track when stars formed and how long they have been evolving. By analyzing the materials in a galaxy, such as the presence of heavy elements, researchers can determine how many generations of stars have lived and died there, each contributing to the galactic environment. Additionally, looking at different galaxies at various distances means we can see light from potentially very early times, acting like a window into the past. This helps build a picture of how galaxies have changed over roughly 14 billion years. By combining this information, scientists can understand the broader story of the universe, including periods of rapid formation and times of relative calm. The study of how galaxies transform over time lays critical building blocks for constructing a narrative about the universe's history, showing us not just how individual galaxies have evolved, but also how the cosmos itself has changed and continues to change. Incredibly distant galaxies act like time machines, offering a glimpse into the early universe. When we observe these galaxies, we are not just seeing them as they are now, but as they were billions of years ago. Light travels immense distances across space, taking a long time to reach us. So by the time we see light from these distant galaxies, we are witnessing a snapshot of a much younger universe. These galaxies help scientists understand how the cosmos evolved and the processes that shaped it. For instance, distant galaxies tend to be smaller and less developed than those we see closer to home. This indicates that gas and dust were still in the early stages of coming together to form stars and planets. Observing the formation of these galaxies provides clues about conditions during the universe's infancy, shortly after its birth, when it was filled with a hot, dense mix of particles. Additionally, studying the light from these galaxies reveals their chemical composition. Scientists can detect elements that are crucial for understanding the life cycle of stars. Elements like hydrogen and helium, which were the building blocks of the universe, are often present in great quantities. Over time, as stars form and evolve, they create heavier elements through nuclear fusion. The abundance of these elements in distant galaxies informs us about stellar processes and how those processes contributed to making the universe rich in diversity. Distant galaxies are invaluable not just for understanding the structure of the universe today, but also for piecing together the story of our cosmic origins. They show us a time when stars were just beginning to light up, illuminating the path of evolution that led to the rich tapestry of galaxies we see now. Through their study, we gain insight into the forces that shaped the universe and our place within it. The discovery of the universe's expansion began with the work of astronomers in the early 20th century. The key player in this breakthrough was Edwin Hubble. He focused on observing distant galaxies through powerful telescopes. What he found was remarkable. The light coming from these galaxies was shifted toward the red end of the spectrum, a phenomenon known as redshift. This redshift indicated that the galaxies were moving away from us. Hubble's observations suggested that the farther a galaxy is, the faster it appears to be moving away. This relationship led to a groundbreaking conclusion. The universe itself is expanding. Instead of remaining static, galaxies are drifting apart over time. Hubble's findings were further supported by the work of other scientists who explored the implications of this expansion. The idea resonated with the predictions made by Albert Einstein's theory of general relativity, which also hinted at a dynamic universe. Together, Hubble's evidence and Einstein's theory formed a new understanding of the cosmos. This discovery reshaped our view of the universe, transforming it from a static model to one of continual growth and change. The realization that we live in an ever-expanding universe opened doors to further exploration of cosmic origins, leading to the Big Bang theory and countless questions about the nature of reality itself. The expansion of the universe is supported by several key pieces of evidence, each adding to our understanding of how the cosmos is changing over time. One of the most pivotal discoveries came from observing distant galaxies. Astronomers found that these galaxies are moving away from us, and the farther away a galaxy is, the faster it appears to be receding. This observation is a result of what we call redshift, where light from these galaxies stretches to longer wavelengths, similar to how a sound might change as something moves away from you. Another significant piece of evidence comes from the cosmic microwave background radiation. This faint glow, present throughout the universe, is the remnant heat from the Big Bang. When scientists studied this radiation in detail, they discovered patterns that indicate a very hot and dense beginning that has been expanding ever since, leading to the cooler universe we see today. Additionally, the abundant presence of light elements, such as hydrogen and helium, aligns with predictions made by the Big Bang theory. When scientists calculated how much of these elements should exist based on the conditions right after the universe began, they found that the amounts observed today match those predictions. Finally, the structures we observe, from galaxies to clusters of galaxies, also provide insight. The distribution and movement of these large-scale structures suggest they have been influenced by expansion over billions of years. When piecing together all these clues, a clear picture emerges. The universe is not static. It is a constantly growing expanse, changing the way we understand our place in it. The expansion rate of the universe plays a crucial role in shaping our understanding of cosmological models. To grasp this, consider how the universe is like a balloon that is inflating. As the balloon expands, every point on its surface moves away from every other point. This behavior illustrates how galaxies move away from each other over time due to the expansion of space itself. The rate at which this expansion occurs is described by something called the Hubble constant. This constant provides insight into how fast celestial objects are receding from us. A higher expansion rate could suggest that the universe is younger than we previously thought, while a lower rate may indicate an older universe. These interpretations help cosmologists establish timelines of the universe's history, including its birth during the Big Bang. Additionally, the expansion rate influences theories about what the ultimate fate of the universe may be. If the expansion continues to accelerate, it could lead to scenarios where galaxies drift away forever, resulting in a cold and lonely universe. Conversely, if the rate slows down, gravity might take over, eventually leading to a collapse, the so-called Big Crunch. Cosmological models are built upon observational data, and the measurements of the expansion rate have implications for the types of dark energy present, which is believed to drive acceleration. Understanding how this expansion connects to various components of the universe, like dark matter and radiation, provides a more complete picture of how everything fits together in our cosmos. Thus, the universe's expansion rate is not just a number. It is a foundational aspect that affects everything from the universe's age and structure to its future. Each new discovery regarding this rate refines our models and deepens our understanding of the vast and complex universe we inhabit. An eternally expanding universe has profound implications for everything we understand about cosmic life and the fate of all galaxies. Imagine a balloon being blown up. As it expands, every point on the surface moves away from every other point. In our universe, galaxies are like the dots on that balloon, gradually drifting apart as space itself stretches. One major consequence of this continuous expansion is that, over immense stretches of time, galaxies that are currently visible may one day disappear from view. As they recede beyond the limits of our vision, the light they emit will take longer to reach us than the universe will have expanded. This means that distant galaxies will become isolated, and ultimately, only a handful of nearby galaxies will remain visible. Additionally, as the universe expands, it cools down. This cooling affects the formation of new stars, as the raw materials are gradually spread thinner across an ever-expanding cosmic fabric. If the trend of expansion continues unabated, we may reach a point where star formation becomes exceedingly rare. Eventually, the energetic life cycles of existing stars will conclude, leading to a dark universe filled with burnt-out stars known as white dwarfs, neutron stars, or black holes. In terms of cosmic evolution, we ponder the so-called heat-death scenario. As galaxies drift apart and stars burn out, the universe will reach a state of maximum entropy, where energy becomes uniformly distributed and no longer able to sustain processes that lead to further change. Life as we know it may cease to exist, making the universe a vast, cold, and empty space. The expansion of the universe also raises fascinating questions about the nature of dark energy, the mysterious force driving this expansion. Understanding dark energy is essential to grasp the universe's future and our own place within it. As scientists continue to explore these cosmic mysteries, the implications of an eternally expanding universe stretch far beyond mere distances. They challenge our conceptions of time, existence, and the ultimate fate of everything in creation. Recent discoveries have significantly deepened our understanding of universal expansion, challenging and refining theories that had stood for decades. For a long time, scientists believed that the expansion of the universe was a steady process, a consistent stretch of space over time. However, observations have revealed that this expansion is accelerating. One of the pivotal moments in this journey came with the observation of distant supernovae, which are massive explosions that occur at the end of a star's life. These cosmic events serve as powerful beacons. When astronomers studied their light, they found that these supernovae were fainter than expected. This meant they were farther away than previously estimated, suggesting that the universe has been expanding at an increasing rate. This acceleration has been attributed to a mysterious form of energy known as dark energy, which seems to make up a substantial part of the universe's total energy content. While dark energy remains elusive, its presence explains why galaxies are moving away from each other more rapidly over time. Instead of slowing down due to gravity, the universe continues to stretch and pull apart. The discovery of the cosmic microwave background radiation also plays a crucial role. This radiation provides a snapshot of the infant universe, showing us how matter and energy were distributed shortly after the Big Bang. As scientists refine their measurements of this radiation, it reveals more about the universe's expansion history, supporting the idea that it has not only expanded, but is doing so at a growing pace. The combination of these different observations has led to the conclusion that our universe is dynamic and continually evolving. Each new finding brings us closer to understanding the nature of space, time, and the enigmatic forces driving the expansion, showcasing the frontier of modern astrophysics where every discovery holds the potential to reshape our view of the cosmos. Neutron stars are one of the most fascinating types of celestial bodies in the universe, distinctly different from stars like our Sun or even black holes. These compact giants are the remnants of massive stars that have run out of fuel and undergone a supernova explosion. During this cataclysmic event, the core of the star collapses under immense gravity, so tightly that protons and electrons combine to form neutrons. This creates an incredibly dense object, where the matter is packed together so tightly that a sugar cube-sized amount would weigh as much as an entire mountain. What makes neutron stars particularly unique is their density and size. They are typically only about 20 kilometers across, yet they can contain a mass greater than the Sun. This means they exhibit some extreme gravitational effects, causing them to warp the space around them. Additionally, neutron stars can rotate at astonishing speeds, sometimes completing several hundred rotations in just 1 second. These rapid rotations can create a beam of radiation that sweeps across space, much like a lighthouse. If Earth stands in the path of this beam, we see the star pulse in a regular pattern, leading to what we call a pulsar. Neutron stars also have strong magnetic fields, millions of times stronger than any magnetic field found on Earth. This contributes to the intriguing emissions of radio waves and other types of radiation that are detected by scientists, allowing us to learn more about these incredible objects. The combination of extraordinary density, rapid rotation, and intense magnetic fields not only sets neutron stars apart from other celestial bodies, but also makes them a key subject of study in understanding the universe's structure and the fundamental laws of physics. Neutron stars are born from the explosive deaths of massive stars, which end their life cycles in spectacular events known as supernovae. When a star much larger than our Sun exhausts its nuclear fuel, it can no longer support itself against the force of gravity. The core of the star collapses under its own weight, compressing until it becomes incredibly dense. This collapse leads to a stage where protons and electrons combine to form neutrons, hence the name neutron star. What emerges from this cataclysm is a small, incredibly dense object, often just about the size of a city, yet containing more mass than the Sun. Neutron stars exhibit fascinating phenomena due to their extreme conditions. One of the most captivating features is their rapid rotation. After the core collapses, conservation of angular momentum causes the star to spin faster, sometimes hundreds of times every second. In addition to their rapid spin, neutron stars possess powerful magnetic fields, which can be trillions of times stronger than Earth's. These magnetic fields can trap charged particles, generating beams of radiation that sweep across the skies. If these beams point towards Earth, we see a pulsating light, leading to the nickname pulsars. This phenomenon occurs because we perceive the signals only when they are directed toward us, much like a lighthouse sweeping its beam across the ocean. Neutron stars also have extraordinary surface gravity, far exceeding that of any planet or even a black hole in some cases. This intense gravity creates extreme conditions that can lead to various unique phenomena, such as the emission of gravitational waves when two neutron stars collide, which can give us insight into the nature of gravity itself and the very fabric of space and time. These stars are not just remnants of stellar evolution, they serve as cosmic laboratories, offering clues about the fundamental laws of physics and the extreme states of matter. Neutron stars are some of the most enigmatic objects in the universe, and they hold many secrets about their composition and behavior. When a massive star exhausts its nuclear fuel, it can collapse under its own gravity. This collapse forms a neutron star, which is incredibly dense, making it only a few kilometers across, but containing more mass than our Sun. At their core, neutron stars are primarily composed of neutrons, which are particles that are normally found within atomic nuclei. What makes these stars so intriguing is how they challenge our understanding of matter. In regular conditions on Earth, we think of atoms as the building blocks of matter. However, within a neutron star, the pressure is so high that it compresses atoms to the point that protons and electrons merge to form neutrons. This transition gives rise to a state of matter that behaves differently than anything we encounter in everyday life. One of the thrilling mysteries surrounding neutron stars is what happens in their outer layers. These layers might exhibit strange properties because of the extreme conditions. Are there substances that defy our normal understanding of physics? Scientists believe that beyond the neutrons, there may exist exotic particles or even strange quark matter, adding another layer of complexity to their composition. The behavior of neutron stars also amazes researchers. They exhibit extraordinary phenomena such as pulsars, which are rotating neutron stars that emit beams of radiation. As these beams sweep across Earth, they create the impression of a lighthouse, allowing scientists to study their rotation speeds. Some neutron stars spin incredibly fast, completing dozens of rotations in just 1 second. What drives this rapid spin, and how does it affect their internal structure? These are questions that remain unanswered. Moreover, when neutron stars collide, they create powerful events known as kilonovae, producing heavy elements like gold and platinum in the process. This throws open another mystery regarding the origins of these precious metals throughout the universe. By studying these events and the properties of neutron stars, scientists are not only piecing together the structure of the universe, but also refining our understanding of the fundamental laws of physics. Neutron stars act as cosmic laboratories, revealing profound insights into the nature of matter and the forces that govern the universe. Each discovery about their composition and behavior deepens our fascination with these celestial objects and our quest to unravel the mysteries of the cosmos. Binary neutron star mergers are cosmic events that provide a wealth of information about the universe. When two neutron stars, incredibly dense remnants of massive stars, spiral towards each other and collide, the result is not only a spectacular explosion, but also an opportunity for scientists to witness the universe in new ways. These mergers release enormous amounts of energy, including gravitational waves, which are ripples in the fabric of spacetime. By detecting these waves, scientists can learn about the nature of gravity and the fundamental properties of the universe. The detection of gravitational waves from binary neutron star mergers marked a groundbreaking moment in astrophysics. For the first time, we could confirm an event through both gravitational waves and electromagnetic signals, such as visible light, gamma rays, and radio waves. This combined observation, often referred to as multi-messenger astronomy, allows astronomers to build a more detailed picture of these events and their after-effects. Furthermore, the heavy elements created during such a merger contribute to the cosmic supply of materials. When the neutron stars collide, they can forge elements like gold and platinum, enriching space. This challenges previous theories about where such elements originate and raises questions about their role in the formation of planets and life as we know it. Studying binary neutron star mergers helps scientists refine their models of stellar evolution and the life cycle of massive stars. This understanding is crucial not only for comprehending the formation and behavior of neutron stars, but also for piecing together the larger story of the universe's evolution, including the expansion of the universe and the behavior of dark matter and dark energy. These cosmic collisions are not just violent explosions, they are gateways to unlocking the mysteries of our universe. Recent discoveries about neutron stars have significantly shifted our understanding of astrophysics, revealing these dense cosmic bodies as incredible laboratories for studying the laws of physics under extreme conditions. A neutron star forms when a massive star runs out of fuel and collapses under its own gravity, transforming its core into an incredibly compact object. These stars are so dense that a spoonful of neutron star material would weigh as much as an entire mountain on Earth. This density allows scientists to study fundamental questions about matter. For instance, the behavior of particles under such pressure has implications for theories about the fundamental forces of nature. One of the most exciting revelations comes from observing neutron star mergers. When two neutron stars collide, they release enormous amounts of energy, which leads to the formation of heavy elements like gold and platinum. Observing these events has provided insights into the origins of elements in the universe, connecting cosmic phenomena to the chemistry that makes up our world. Additionally, the study of gravitational waves emitted during these mergers has opened a new window in astrophysics. Gravitational waves are ripples in space-time created by massive objects accelerating through space. This allows scientists to detect and study events that would otherwise be invisible, expanding our understanding of the universe's evolution. Neutron stars also help illuminate the mysteries of dark matter and dark energy, two aspects that make up much of the universe but remain largely elusive. By investigating the behaviors and interactions of neutron stars, researchers are piecing together clues that could reveal more about these enigmatic components. Recent findings on neutron stars have not only deepened our knowledge of the life cycles of stars, but have profoundly influenced various areas of astrophysics, from the behavior of matter and the creation of heavy elements to the evolution of the universe itself. Each discovery acts as a stepping stone, taking us closer to solving some of the cosmos's greatest mysteries. A supernova is a powerful explosion that occurs at the end of a star's life cycle. This dramatic event can be caused by different mechanisms, leading to two main types of supernovae. The first type involves massive stars, those many times larger than our Sun. When these stars exhaust their fuel, they can no longer support their own weight. The core collapses under gravity, reaching incredible densities, while the outer layers rebound and explode outward, creating a supernova. The second type, called a Type 1 supernova, involves a different scenario. This occurs in binary systems where one star is a white dwarf, the remnants of a smaller star that has already undergone its own transformation. If this white dwarf gathers too much material from its companion star, it can reach a critical mass, causing a runaway nuclear reaction that results in a violent explosion. Supernovae are more than just cataclysmic events. They play crucial roles in the universe. They create and disperse heavy elements, scattering them across space. These elements ultimately contribute to the formation of new stars and planets. Furthermore, the remnants of supernovae can become neutron stars or even black holes, depending on their mass. Each type of supernova contributes to the cosmos in unique ways, shaping the structure and evolution of galaxies. Supernovae are spectacular explosions that mark the end of a star's life cycle, and their impact on the surrounding cosmos is profound. When a massive star exhausts its nuclear fuel, it can no longer support its own weight and collapses inward, triggering a violent explosion. This explosion releases an enormous amount of energy, scattering the star's outer layers into the space around it at incredibly high speeds. These ejected materials enrich the surrounding cosmic environment with heavy elements like carbon, oxygen, and iron, ingredients essential for life and the formation of new stars and planets. Imagine the supernova as a cosmic fertilizer, seeding the universe with materials that will eventually contribute to the birth of new stars. Additionally, this explosive event generates shock waves that ripple through the interstellar medium. These shock waves compress nearby gas and dust, triggering the formation of new stars. This process is akin to a cosmic chain reaction, where the remnants of older stars breathe life into a new generation of celestial bodies. Moreover, supernovae release tremendous amounts of energy in the form of radiation, which can influence the climate of nearby celestial bodies. When a star goes supernova close enough to a planet, the intense radiation can strip away an atmosphere or create conditions that could restrict the development of life. Supernovae play a critical role in the cosmic ecosystem. They not only generate new materials essential for star and planet formation, but also affect the dynamics of their surroundings, setting the stage for the continual cycle of creation and destruction that defines the universe. Their influence reaches far beyond their explosive moments, leaving a lasting legacy in the cosmos. Supernovae are stellar explosions that occur at the end of a massive star's life cycle, and they play a crucial role in shaping the universe. When a massive star runs out of nuclear fuel, it can no longer support its own weight, causing it to collapse under gravity. This collapse leads to an explosive outburst, ejecting the star's outer layers into space. This explosion is not just a spectacular event, it has profound consequences for the cosmos. The material expelled during a supernova is rich in elements heavier than hydrogen and helium, such as carbon, oxygen, and iron. These elements are fundamental to the formation of new stars and planets. As the shock wave from the explosion travels through space, it compresses surrounding gas and dust. This compression can trigger the process of star formation in nearby regions of space, leading to the birth of new stars from the dense clouds of material that gather together. Moreover, supernovae contribute to the chemical enrichment of the universe. Newly formed stars, which often originate from the remnants of earlier supernovae, contain these elements. When these stars eventually end their lives, they too may explode as supernovae, continuing the cycle of creating and spreading materials necessary for forming planetary systems and complex structures within galaxies. Additionally, supernova explosions can influence the structure of galaxies themselves. The energy released can create shock waves that affect the surrounding interstellar medium, which is the gas and dust that fills the space between stars in a galaxy. This interaction can lead to the formation of new star clusters, or even influence the dynamics and evolution of the galaxy as a whole. Supernovae are essential in the cosmic dance of life and death, generating the very building blocks of stars and galaxies, while also helping to orchestrate the environment in which they form and evolve. Supernovae are brilliant explosions that mark the death of a star, and they serve as cosmic signposts for scientists trying to understand the universe. When a massive star runs out of nuclear fuel, it can no longer support itself against its own gravity. This leads to catastrophic collapse and a subsequent explosion that releases an extraordinary amount of energy. The light from a supernova can outshine entire galaxies for a short time, allowing astronomers to observe these events across vast distances. One of the main insights that supernovae offer is about the life cycle of stars. By studying the different types of supernovae, scientists can learn about the processes that lead to stellar death. There are two primary types: core collapse supernovae from massive stars and type Ia supernovae that result from a white dwarf gaining mass. Each type has distinct characteristics, and understanding them deepens our knowledge of stellar evolution. Supernovae are also important for investigating the expansion of the universe. In the late 20th century, scientists observed that certain types of supernova, especially the type Ia variety, appear dimmer than expected when they are very far away. This unexpected dimming implies that these distant objects are farther away than earlier models predicted, suggesting that the universe's expansion is accelerating. This has led to the discovery of dark energy, a mysterious force driving this acceleration. Moreover, supernovae create and distribute heavy elements throughout the universe. When these massive stars explode, they forge a variety of elements like iron, gold, and uranium, which are then scattered across space. This process enriches the material in interstellar clouds, which will eventually form new stars and planets, including our own. Essentially, every atom in our bodies was likely created in the heart of a star that exploded long ago. Supernova act as natural laboratories for scientists. They provide critical information about star life cycles, help unveil the mysteries of cosmic expansion, and are essential for understanding the chemical evolution of the universe. Each explosion brings with it a treasure trove of data, shaping our comprehension of the cosmos. Supernovae are among the most powerful explosions in the universe, and they hold many secrets that pique scientists' curiosity. One of the primary mysteries is the exact mechanisms that lead to these colossal eruptions. There are different types of supernovae, and understanding the nuances of how each one forms remains a challenge. For instance, while some arise from the collapse of massive stars when they exhaust their nuclear fuel, others occur in binary systems, where one star siphons material from its companion until an explosion is triggered. Unraveling these processes can unveil much about stellar life cycles and the dynamics of star systems. Another significant mystery revolves around the elements produced during these explosions. Supernovae are responsible for forming many of the heavier elements we see in the universe, such as gold and uranium. Scientists are eager to learn how these elements are created and distributed through space, as this plays a crucial role in the formation of planets and life itself. Understanding the distribution of these materials also helps in piecing together the history of our galaxy. Furthermore, there is the enigmatic phenomenon of dark energy and its connection to supernovae, specifically in the context of cosmic expansion. Observations of distant supernovae have helped researchers understand that the universe is not only expanding but also accelerating in that expansion. Scientists want to deepen their knowledge of how supernovae can serve as precise markers for measuring cosmic distances and what this means for our understanding of the universe's fate. Lastly, studying supernova remnants, the leftover material after the explosion, can provide insights into the conditions of the early universe and the formation of new stars and galaxies. These remnants are like cosmic laboratories that help scientists study how matter interacts after such a catastrophic event. The exploration of supernova touches on a variety of scientific fronts, from stellar processes and element creation to the broader cosmic questions of our universe's evolution and acceleration. Each mystery solved brings us closer to understanding the grand tapestry of existence. Cosmic voids are vast empty spaces in the universe where very few galaxies are found. Imagine the universe as a gigantic sponge, with the galaxies and galaxy clusters acting as the dense bits of matter that make up the sponge's structure. The areas without matter, the voids, correspond to those empty spaces where not much is happening. These voids can be enormous, stretching for hundreds of millions of light years across. They are surrounded by walls of galaxies and galactic clusters that create a web-like structure, often referred to as the cosmic web. In this web, most matter is concentrated along filaments, which are strings of galaxies, while the voids lie in between. The existence of cosmic voids plays a vital role in our understanding of the universe's evolution. As the universe expands, the distribution of matter changes. Voids grow larger over time because the force of gravity pulls galaxies and matter toward each other, leaving these vast areas largely empty. Studying cosmic voids helps astronomers learn about dark energy, the mysterious force thought to be driving the universe's accelerated expansion. Since voids contain fewer galaxies, they provide a unique opportunity to observe the large-scale structure of the universe without interference from densely packed areas. Cosmic voids are not just empty spaces, they are fundamental pieces in the puzzle of the universe's organization and development. Cosmic voids, which are vast empty spaces in the universe, were first recognized in the late 20th century. Astronomers were initially examining the distribution of galaxies. As they mapped out these galaxies, they noticed significant gaps between them. This observation prompted further exploration of these seemingly barren regions, leading to the identification of larger structures within the cosmos. These voids can be understood as part of the overall framework of the universe. It's as if galaxies are scattered across the surface of a sponge, with the voids representing the holes. As scientists studied these patterns, they discovered that cosmic voids often exhibit a structure that resembles a web-like arrangement, known as the cosmic web. This web includes clusters of galaxies, filaments connecting them, and large voids where very few galaxies can be found. Interestingly, voids are not entirely empty. They can contain some matter, including dark matter and gas, but at much lower densities than the areas where galaxies are densely packed. Over time, researchers found that these voids tend to be larger than initially thought. They can span hundreds of millions of light years, influencing the motion of galaxies that inhabit the nearby regions. Additionally, scientists discovered that voids can have certain patterns in their sizes and shapes, often appearing more elongated than spherical. Some theories suggest that these patterns reflect the early conditions of the universe shortly after the Big Bang. As gravity pulled matter together, regions with slightly higher densities formed clusters, while lower density areas turned into these cosmic voids. Understanding cosmic voids is vital, as they provide insight into the fundamental nature of our universe, its evolution, and the mysterious fabric of dark energy and dark matter that shapes it. The vast emptinesses of the universe, often referred to as cosmic voids, hold many mysteries about their formation and evolution. These voids are not just empty spaces, they are intricate structures that tell us a lot about the development of the universe itself. Imagine the universe as a giant web, where galaxies and clusters of galaxies are like beads strung along the threads, while the spaces in between represent these voids. One of the fundamental questions scientists grapple with is how these voids formed in the first place. Initially, in the early universe, matter was distributed quite evenly. However, over billions of years, gravity began to pull matter together, leading to the formation of dense regions where galaxies could cluster. The areas that did not attract enough matter evolved into empty expanses, resulting in the voids we observe today. Essentially, they are the remnants of this galactic pull, where lesser matter congregated or remained scattered. Another aspect of these voids' evolution is their size and shape. Some voids are huge, spanning millions of light years, while others are smaller but still significant in size, showcasing a variety of forms. Their sizes are thought to be influenced by the distribution of dark matter, an invisible substance that constitutes much of the universe's mass. This dark matter acts like an unseen hand, shaping how voids develop over vast timescales. As researchers examine voids, they also contemplate their role in cosmic evolution. For instance, voids can affect the formation of galaxies. The gravitational pull of nearby regions can lead to galaxy interactions, while the emptiness of a void may have less impact, resulting in fewer galaxies forming there. This creates a unique environment that can influence the life cycles of galaxies and how they evolve over time. Moreover, exploring these voids offers insight into fundamental questions about the universe's overall structure and its fate. The cosmic microwave background radiation, the afterglow of the Big Bang, shows patterns that can be linked to void formation. Understanding these patterns can shed light on the amount and nature of dark energy, a mysterious force thought to drive the universe's accelerated expansion. The cosmic voids are not just nothingness. They carry profound implications about the universe's history and future, acting as a canvas on which the story of cosmic evolution is painted. These regions challenge our understanding of gravity, matter, and the very fabric of the universe itself, making their study both intriguing and essential for unlocking the cosmos's deepest secrets. In the vastness of the universe, there are regions known as cosmic voids, which are large, empty spaces containing very few galaxies. These voids present a fascinating challenge to current models of the universe. Traditionally, scientists understood the cosmos as a tapestry woven with galaxies, clusters, and filaments, forming a structure reminiscent of a web. The existence of these voids suggests that the distribution of matter is far more complex than once believed. The challenge posed by cosmic voids comes from their size and frequency. When astronomers survey the universe, they find that these voids are not just isolated pockets of emptiness, but are actually a critical part of the cosmic landscape. They cover a substantial portion of the universe and can span millions of light years in diameter. This extensive emptiness contradicts earlier models, which assumed a more uniform distribution of matter. Another aspect is the gravitational effects that cosmic voids have on surrounding areas. Where matter is absent, gravitational forces behave differently. These voids impact how galaxies form and evolve, leading scientists to reevaluate the nature of gravity and dark energy. Dark energy, which is thought to be driving the universe's expansion, interacts differently in and around these voids, prompting physicists to reconsider their understanding of its role. Cosmic voids also challenge the concept of large-scale structure formation in the universe. The scale and influence of voids mean that they can affect the trajectory of galaxies, altering expectations for how and where galaxies should exist. This leads to new questions about the origins of these voids and their influence on the early universe after the Big Bang. In conclusion, cosmic voids encourage a re-examination of our current theories about the universe. They push scientists to refine existing models and consider new physical principles to accurately describe the unseen forces at play in the grand and intricate cosmos. The study of these voids continues to reshape our understanding of everything from cosmic evolution to the fundamental nature of the universe itself. Cosmic voids are vast, empty spaces in the universe that contain very few or even no galaxies. Understanding these massive gaps can significantly impact our cosmological theories, as they provide insights into the large-scale structure of the universe and how it has evolved. First, voids reveal a lot about dark matter, which makes up much of the universe's mass but cannot be seen directly. The behavior of matter is influenced by these voids as they exert less gravitational pull compared to regions filled with galaxies. By studying how galaxies cluster around voids, scientists can refine their models of dark matter, figuring out how it interacts with regular matter and its overall distribution throughout the cosmos. Furthermore, the existence and characteristics of voids can help improve our understanding of cosmic expansion. The universe is constantly stretching, and voids appear to grow over time. By examining this expansion and the rate at which voids develop, researchers can gather evidence about the forces driving the universe's acceleration, including the mysterious dark energy thought to be responsible for this phenomenon. Additionally, studying voids can reveal information about the conditions of the early universe. Their formation offers clues about the density fluctuations that occurred after the Big Bang. This can lead to a more accurate picture of how our universe formed and evolved into the complex structure we observe today. Overall, cosmic voids are not just empty spaces, they are key players in the universe's narrative. By understanding them better, we can reshape or enhance existing theories about the universe's composition, expansion, and underlying forces. This knowledge could ultimately lead to breakthroughs that deepen our connection to the cosmos and our place within it. Superclusters are vast formations in the universe that group together numerous galaxy clusters, which are themselves collections of millions of stars, planets, and other celestial bodies. To understand this concept, picture a neighborhood filled with houses. Each house represents a galaxy, and the neighborhood represents a galaxy cluster. Now, imagine several neighborhoods close to each other forming a larger community. That community is a supercluster. The sheer size of a supercluster can be mind-boggling. While a typical galaxy cluster might span tens of millions of light-years, superclusters can extend to hundreds of millions or even billions of light-years across. This means they can contain hundreds or thousands of galaxy clusters within their boundaries. This larger scale fundamentally changes the way we view the structure of the universe, organizing it into a vast web of interconnected galaxies and clusters. Superclusters are not evenly distributed. They lie along vast filaments of galaxies, forming the backbone of the universe's structure. This formation occurs under the influence of gravity, which pulls matter together in a cosmic dance. The space between these superclusters is largely empty, creating vast voids. Observing these formations allows astronomers to better understand the formation of the universe, its expansion, and the distribution of dark matter, which remains a mystery. Superclusters represent the largest known structures in the universe, surpassing standard galaxy clusters in both size and complexity. They highlight the grand scale of cosmic architecture, revealing how the universe evolves and remains interconnected through gravitational forces. Scientists study superclusters by observing their massive structures and understanding their influence on the universe's framework. Superclusters are vast groups of galaxies bound together by gravity, and determining their role begins with mapping their locations in the sky. By using powerful telescopes equipped with advanced imaging techniques, researchers can track the light from galaxies within these superclusters, allowing them to see how these colossal structures shape their surroundings. The next step involves analyzing the light emitted or absorbed by these galaxies. Different wavelengths of light offer insights into the composition and behavior of the galaxies, helping scientists understand their movements and interactions. This information can reveal how superclusters affect the flow of matter and energy in the universe, influencing the formation of galaxies and the distribution of dark matter, a mysterious component that makes up most of the universe's mass but cannot be seen directly. To comprehend their relationship with the broader universe, scientists utilize simulations alongside their observational data. By creating computer models that replicate cosmic development, they analyze how superclusters grew over billions of years and how they interact with other cosmic structures, such as voids, vast empty areas devoid of galaxies. Furthermore, by studying the cosmic microwave background radiation, the afterglow of the Big Bang, scientists gain vital clues about the overall architecture of the universe. Variations in this ancient light indicate how matter was distributed early on, including regions that would later evolve into superclusters. Through a combination of observation, analysis, and simulation, scientists unravel the crucial role superclusters play, helping to confirm theories of cosmic evolution and enhancing our understanding of how this grand structure continues to evolve today. This ongoing research not only reveals the intricate tapestry of the universe, but also deepens our appreciation of our place within it. Superstructures are vast cosmic formations like galaxy clusters that reveal profound mysteries about dark matter and the nature of gravity in the universe. Imagine viewing a sprawling city from above. The layout and connections show how it functions and grows. In the same way, the arrangement of superstructures helps scientists understand the underlying forces at play in the universe. One of the key observations is that galaxy clusters contain far more mass than what is visible in ordinary matter, like stars, planets, and gas. This discrepancy suggests the presence of dark matter, a type of matter that does not emit or absorb light and is invisible to telescopes. Dark matter is theorized to make up a significant portion of the universe's total mass, acting as a scaffolding that holds these massive structures together. Without it, galaxies wouldn't form as we see them today, and their movement would be entirely different, falling short of our observations. When investigating superstructures, scientists also look at gravity's role. Traditional understanding of gravity, as described by physics, is based on how mass attracts other mass. However, the significant influence of dark matter alters this picture. Superstructures challenge scientists to rethink gravity's behavior at large scales. They suggest that gravity may not act exactly as we expect over these immense distances, pushing researchers to explore theories that could bridge our comprehension of gravitational forces and the elusive nature of dark matter. Furthermore, the distribution of superstructures offers clues to the very fabric of space-time. The gravitational lensing effect, where light from distant objects is bent around a massive structure, acts like a cosmic magnifying glass, revealing the presence of dark matter surrounding the superstructure. This lensing helps scientists map dark matter's distribution, even if it remains hidden in the night sky. Superstructures serve as cosmic puzzles, intertwining the concepts of dark matter and gravity. They enable researchers to probe deeper into the universe's workings, urging us to question and refine our understanding of both the seen and the unseen forces that shape our cosmos. Superclusters are among the largest structures in the universe, consisting of groups of galaxies bound together by gravity. Their distribution plays a significant role in shaping the overall cosmological landscape. To understand this, think of the universe as a vast three-dimensional web. This web is made up of numerous strands and intersections, representing different structures. Superclusters are the dense areas in this web, while the spaces in between are more sparse. The locations of superclusters influence the way galaxies form and evolve. When galaxies are close together in these superclusters, they share resources like gas and dark matter, which can lead to higher rates of star formation. This means more suns and ultimately more planets, which could be crucial for the development of life. Additionally, the gravitational pull of superclusters can affect the motion of galaxies. They act like gravitational lenses, bending light from more distant objects and affecting how we observe the universe. This lensing can reveal information about the hidden mass, such as dark matter that we cannot see directly but is essential for understanding the universe's structure. More broadly, the distribution of superclusters can reveal insights into the history and future of the universe. By studying the arrangement and density of these superclusters, scientists can learn about the expansion rate of the universe and the forces that shape its evolution. It's like mapping out the growth patterns of a plant. By observing where it flourishes or struggles, we can infer the conditions around it. Superclusters are not merely clusters of galaxies, they shape the cosmic landscape in profound ways. Their gravitational influences affect galaxy formation, movement, and even our understanding of the universe's past and future. By unlocking their secrets, we gain deeper insights into the very fabric of our cosmos. Recent observations of the universe have significantly advanced our understanding of cosmic superstructures, which are vast formations that span billions of light years and include massive clusters of galaxies. These superstructures, such as galaxy filaments and voids, create a web-like structure throughout the universe, which scientists have only begun to untangle. Using powerful telescopes and advanced technology, astronomers can now capture detailed images and data from deep space. This allows researchers to map the distribution of galaxies and dark matter, revealing how these superstructures are interconnected. Imagine a cosmic spiderweb where each strand represents galaxies that are linked through gravity, forming intricate patterns across the universe. Such mapping helps scientists understand not only the locations of galaxies, but also how they are influenced by the gravitational pull of surrounding structures. Additionally, new observational techniques have improved our ability to study the cosmic background radiation. This ancient light, left over from the Big Bang, carries information about the early universe and helps us understand how superstructures have evolved over time. By analyzing this radiation, astronomers can infer how regions of higher and lower density formed, leading to our present-day cosmic architecture. These observations also shed light on the role of dark energy, a mysterious force that seems to be driving the acceleration of the universe's expansion. As scientists piece together the behaviors of superstructures in relation to dark energy, they gain insights into the ultimate fate of the universe. These recent observations not only enhance our understanding of how galaxies are grouped and arranged, but also improve our grasp of the underlying forces that shape our universe. As we continue to probe deeper into space, each discovery adds another layer to this grand cosmic narrative, helping us uncover the mysteries of our vast universe. Wormholes are fascinating hypothetical structures that scientists speculate might exist in the fabric of space-time. To understand them, think of space-time as a vast, three-dimensional fabric that strengthens when you pull it tight. Now picture 2 points on this fabric, which could be far apart in the universe. If you were to travel the normal way, it would be like traveling across an extended distance. However, if a wormhole exists, it would allow you to fold that fabric and connect those 2 points almost directly, as if you were drawing a straight line between them. The beauty of a wormhole lies in its potential to act as a shortcut. Imagine if you could move from one location in space to another much further away without covering the usual distance between them. Instead of following the traditional path that might take years, a journey through a wormhole could occur in a matter of moments. This idea arises from the equations of general relativity, which describes how gravity and space interact. However, it's important to note that wormholes are still theoretical. No one has yet found direct evidence of their existence. Scientists believe that if they do exist, they might be unstable and could potentially collapse before anything could traverse them. Furthermore, crossing a wormhole could introduce strange scenarios, such as jumping to alternate realities or facing unknown forces. Despite these challenges, the allure of wormholes captured our imagination, showcasing the ever-mysterious nature of the universe. The concept of wormholes is deeply rooted in the theories of physics that describe the fabric of the universe. At the heart of this idea is Albert Einstein's theory of general relativity. This theory explains how massive objects like stars or black holes warp the space around them, creating what we perceive as gravity. General relativity allows for solutions that suggest the possibility of shortcuts through space-time, which we refer to as wormholes. Think of space-time as a flexible sheet. When you place heavy objects on it, like planets, the sheet bends around them. If you could bend the sheet in such a way that 2 points touch, you would create a bridge between them, allowing for rapid travel from one side to the other. This is essentially how wormholes are theorized to work, connecting distant locations in the universe by bending and folding the dimensions of space and time. Beyond Einstein's theories, further developments in theoretical physics, particularly in the realm of quantum mechanics and string theory, have explored the idea of wormholes as well. These fields suggest that the universe might have hidden dimensions and properties, providing a broader framework in which wormholes could exist. Scientists theorize that if such structures were part of our universe, they could give rise to fascinating phenomena such as parallel universes or alternate realities. Despite these intriguing theories, the existence of wormholes remains speculative due to the lack of experimental evidence. Creating or stabilizing a wormhole would require exotic matter, substances with negative energy density, which have yet to be discovered. Without tangible proof or a deeper understanding of the underlying physics, wormholes remain an exciting theoretical possibility rather than a confirmed aspect of our universe. Wormholes are fascinating theoretical structures that scientists propose might function as shortcuts across the universe. To picture this concept, think of space as a vast, flat sheet where distances between points can be incredibly vast. Now imagine if you could bend that sheet so that 2 points touch, creating a tunnel through the fabric of space. This tunnel represents a wormhole, connecting two distant locations in a much shorter path than traveling through regular space. If wormholes exist, they could enable instant travel between far-off galaxies or even different points in time, transforming the way we understand movement through the cosmos. While the idea is intriguing, the journey through a wormhole presents problems. For instance, the laws of physics we understand may not hold inside such structures, leading to unpredictable consequences for anything attempting to traverse them. Additionally, maintaining the stability of a wormhole might require materials or forces that are not currently known to humanity. It's also important to note that traversing a wormhole could expose travelers to intense gravitational forces, potentially making the experience perilous. So while wormholes capture our imagination as cosmic bridges, the reality of traversing them, if they exist, would be more complicated than we can easily fathom. Exploring these ideas pushes the boundaries of our understanding of the universe and the mysteries it holds. Exploring wormholes presents a series of daunting challenges that blend theoretical physics with practical limitations. First, the existence of wormholes is largely hypothetical. They arise from solutions to Einstein's equations of general relativity, but have never been observed or confirmed to exist in our universe. Without empirical evidence, it is difficult to understand their properties or how they might behave. Even if wormholes do exist, there are significant concerns regarding their stability. Many scientists believe that these corridors through space-time would be inherently unstable, collapsing quickly unless held open by a form of exotic matter. Exotic matter is a theoretical substance that possesses negative energy density, which could counteract gravitational pull. However, such matter has not been discovered, leaving us in a realm of speculation. Then there's the question of traversability. If a wormhole could be entered, traveling through it might expose travelers to severe gravitational forces and radiation, potentially leading to dangerous conditions. Would it be safe? Would the journey cause destruction or disorientation? These uncertainties create hesitation in considering actual exploration. Moreover, the craft required for traveling through a wormhole would need to withstand unknown stresses and possibly develop technologies far beyond our current capabilities. We are still developing reliable space travel vehicles capable of reaching even our closest planetary neighbors, let alone navigating through a wormhole. Lastly, the implications of wormhole travel challenge our understanding of causality, the relationship between cause and effect. If one could traverse vast distances instantly, it raises questions about time travel and the potential for paradoxes, where actions in the past could alter the future in ways we cannot predict. Thus, while wormholes spark the imagination with their potential for quick travel across the cosmos, the practical exploration remains a profound puzzle filled with scientific, technical, and philosophical obstacles. Advancements in wormhole research hold the potential to transform the very essence of space travel, reshaping how we understand the cosmos. At its core, a wormhole can be likened to a tunnel that links two separate points in the universe. If scientists could create or identify a stable wormhole, it would mean that we could traverse vast distances in a fraction of the time typically required by conventional means. Imagine embarking on a journey to a distant star that would normally take many years, perhaps even decades with our current technology. With a wormhole, the long trip could become a matter of moments. This could open up exploration to far-off galaxies, allowing for more extensive research and possibly even the discovery of new worlds. We could observe planets that are currently light years away from us, searching for signs of life or new resources to fuel human advancement. Additionally, the implications go beyond mere speed. The unique structure of a wormhole might allow for the transport of not just spacecraft, but also information and materials. This would revolutionize not only how we travel, but also how we communicate across great distances, akin to instant messaging through the universe. However, these advancements come with significant challenges. We still need to understand how to create, stabilize, and navigate such structures safely. Theoretical concepts illustrate a captivating possibility, but practical application remains elusive. Ongoing research into the intricacies of space-time, gravity, and quantum mechanics is necessary to bring these theories closer to reality. If successful, wormhole research could not only accelerate our journey to the stars, but also redefine humanity's place in the universe. Cosmic rays are high-energy particles that travel through space and reach Earth from various sources beyond our atmosphere. Imagine them as tiny, charged bullets shooting across the universe. These particles primarily consist of protons, which are positively charged particles found in atomic nuclei, but they can also include heavier atomic nuclei and even some electrons. What makes cosmic rays fascinating is their origin. They come from immense cosmic phenomena, such as exploding stars or supernova, and even from the sun. When cosmic rays enter our atmosphere, they don't just pass through unnoticed. Instead, they interact with the gases in the air, producing a cascade of secondary particles that can sometimes reach the ground. Picture throwing a stone into a calm pond and watching the waves ripple outward. Similarly, when a cosmic ray strikes an atom in the atmosphere, it can create a surge of new particles, including electrons and neutrinos. This chain of reactions leads to the creation of a shower of particles, which is how we can detect cosmic rays. The interactions of cosmic rays can also provide us with valuable insights into the universe. For instance, studying them helps scientists understand the conditions in extreme environments, such as near black holes or during supernova explosions. Some cosmic rays also carry information about their source, revealing clues about powerful cosmic events, like how stars form and evolve. Additionally, cosmic rays pose challenges for space travel, since they can damage spacecraft and pose risks to astronauts over extended periods in space. Cosmic rays are more than just fast-moving particles. They are messengers from the universe, offering glimpses into the processes that shape the cosmos, while also illustrating the complex interactions that occur when these high-energy particles meet our planet. Detecting and measuring cosmic rays is a fascinating process that involves sophisticated technology and a network of instruments. Cosmic rays are high-energy particles that come from outer space, primarily protons, and heavier atomic nuclei. When these particles enter Earth's atmosphere, they collide with air molecules, creating a cascade of secondary particles. Scientists use different methods to capture these cosmic rays. One common approach involves ground-based detectors. Imagine a large field filled with devices that can sense the showers of particles created when cosmic rays interact with the atmosphere. These detectors often include arrays of sensitive sensors that can identify the energy and trajectory of the arriving particles. By analyzing data from many events over time, scientists can infer the original cosmic ray's energy and direction. Another method is through space-based observatories. These are equipped to directly measure cosmic rays before they reach the atmosphere. Satellites and instruments on spacecraft, like those found on the International Space Station, detect cosmic rays as they travel through space. These instruments can analyze the types of particles and their energy levels as they strike the detector, providing valuable information about their origin and behavior. Additionally, scientists sometimes use specialized materials, such as thick layers of water or ice, to observe the secondary particles produced by cosmic rays. By assessing how far these secondary particles travel and how much energy they lose before being detected, researchers can gain insights into the properties of the original cosmic ray. This combination of technologies allows scientists not just to measure cosmic rays, but to understand their sources, which may include supernovae, active black holes, and other energetic phenomena in the universe. Through continuous monitoring and data collection, researchers are building a clearer picture of these elusive cosmic travelers and their role in the broader cosmos. Cosmic rays are high-energy particles that travel through space, constantly bombarding Earth. They present several intriguing mysteries regarding where they come from and what they are made of. To begin with, most cosmic rays are protons, which are the building blocks of atomic nuclei, but they also include heavier particles like helium nuclei and a diverse mixture of other atomic fragments. One of the key questions surrounding cosmic rays is their origin. Some are believed to come from our own sun, especially during solar flares, while others are thought to originate from more powerful cosmic events, such as exploding stars called supernova or the eruptions of black holes. However, pinpointing the exact source of many cosmic rays remains challenging. They travel vast distances across the galaxy and can be deflected by magnetic fields, making it difficult for scientists to trace them back to their origins. Additionally, the energies of cosmic rays can reach extreme levels, so high that they challenge our understanding of physics. Some rays are thought to originate from sources that release energy far beyond any known man-made particle accelerator. This leads to the question of what kinds of astronomical phenomena can produce such powerful particles. Understanding these sources could shed light on highly energetic events and even the mechanics behind the very fabric of the universe itself. Moreover, scientists are also examining the composition of cosmic rays. While the majority are protons, the presence of heavier nuclei suggests that cosmic rays evolve through complex interactions. They may collide with other particles in the universe, gaining energy and changing their form. Research into cosmic rays not only helps unravel the events that generate them, but also provides insights into fundamental questions about matter and energy in the cosmos. As researchers continue to explore the origins and characteristics of cosmic rays, they unlock secrets about the universe's high-energy processes, revealing not just the mysteries of these particles, but also deeper questions about the universe's nature and our place within it. Cosmic rays are fascinating phenomena that greatly enhance our understanding of high-energy particle physics. These are high-energy particles that originate from outer space and travel through the universe at nearly the speed of light. When they reach Earth, they interact with our atmosphere, creating a cascade of secondary particles that help scientists study their properties. One important aspect of cosmic rays is that they provide insights into the fundamental nature of matter and energy in ways that we cannot replicate on Earth. In particle accelerators, researchers create high-energy collisions to study particles at extreme speeds, but cosmic rays naturally achieve even higher energies as they collide with particles in our atmosphere. By analyzing the particles produced from these collisions, scientists can learn about interactions that would otherwise be difficult or impossible to reproduce in a lab. Additionally, studying cosmic rays helps us understand the sources of these high-energy particles. They are believed to come from various astronomical events such as supernovae, neutron star mergers, or even black holes. Each of these sources involves incredible amounts of energy and contributes to our knowledge of cosmic events and their role in the universe. Furthermore, cosmic rays play a significant role in exploring the very fabric of the universe, including the properties of fundamental particles like protons and neutrons. They can influence theories about dark matter and the expansion of the universe, pushing the boundaries of what we know about the cosmos. Cosmic rays act as a natural laboratory for exploring high-energy physics. Their study reveals interactions at levels not easily accessible through terrestrial experiments, deepening our understanding of the universe and the fundamental forces that shape it. Future research into cosmic rays is set to be multifaceted, diving deeper into their origins and effects in the universe. Scientists are particularly interested in understanding where these high-energy particles come from. Some theories suggest that they may originate from supernova explosions or massive black holes, but confirming these ideas is no easy task. To tackle this, new observatories and detectors are being developed around the world, each with unique capabilities. For instance, some projects aim to build vast arrays of sensors that can detect the faintest light produced when cosmic rays collide with the atmosphere, providing clues about their energy and direction. By tracking these particles back to their sources, researchers hope to gain insights into extreme astrophysical phenomena. Additionally, advances in space-based experiments will enable scientists to study cosmic rays without the distortions caused by Earth's atmosphere. Satellites equipped with specialized instruments will help map the energy spectrum of cosmic rays, allowing for a better understanding of their composition and behavior as they travel across vast distances. Researchers will also explore the interactions of cosmic rays with the particles in our atmosphere, which could reveal how these high-energy events impact climate and weather patterns over time. This investigation presents an intriguing intersection between astrophysics and earth sciences. Through these diverse approaches, the scientific community aims to unravel cosmic rays' intricate mysteries. Every discovery can potentially change our understanding of high-energy processes in the universe, reinforcing the quest to comprehend the fundamental workings of our cosmos. Magnetars are a fascinating type of neutron star, distinguished by their incredibly intense magnetic fields. While all neutron stars are remnants of supernova explosions, magnetars take this to an extreme. Imagine a neutron star, which is already incredibly dense, packed with more mass than the Sun into a sphere just a few kilometers wide. Now, add to that the strongest magnetic field known in the universe, which can be 1,000 billion times stronger than Earth's. These powerful magnetic fields influence their surroundings in extraordinary ways. For instance, magnetars can emit intense bursts of high-energy radiation, which can be many times more powerful than the radiation produced by typical neutron stars. This emission occurs in the form of gamma rays, which are among the most energetic forms of light, and can be detected across vast distances in space. Moreover, this magnetic strength is responsible for unique phenomena such as starquakes, which are sudden shifts in the star's crust that can release enormous amounts of energy. The interplay between gravity and magnetism in magnetars creates a unique environment, leading to interactions that are not seen in other celestial objects. The immense pressure and heat near these stars result in a complex and violent atmosphere. What sets magnetars apart is not just their origins as neutron stars, but their remarkable magnetic fields and the energetic processes they trigger, making them one of the most extreme environments in the cosmos. Magnetars are fascinating celestial objects known for their incredibly strong magnetic fields, which are millions of times more powerful than those found on Earth. These extreme magnetic fields heavily influence how magnetars behave and interact with their surroundings. Imagine a magnetic field so intense it affects everything around it, even altering the fabric of space itself. One of the most noticeable effects of a magnetar's magnetic field is its impact on the behavior of surrounding matter. This immense magnetic force can influence the movement of charged particles, causing them to spiral and accelerate along the magnetic lines. As they do so, they produce high-energy radiation, including X-rays and gamma rays. These intense emissions can be observed from vast distances, allowing us to detect magnetars even when they are located far from our planet. Additionally, the magnetic fields of magnetars can cause the crust of the neutron star, which is already incredibly dense, to crack and shift. This fracturing releases bursts of energy known as magnetar flares. These flares are among the most powerful explosions in the universe, creating shock waves that can affect the surrounding space and even reach Earth. When a magnetar releases energy in this way, it can momentarily outshine entire galaxies, showcasing the raw power contained within. Magnetars can also experience gradual changes in their magnetic fields over time, a phenomenon known as magnetic field decay. This process contributes to their overall behavior and can lead to changes in their emission patterns. As the magnetic field weakens, the magnetar may become less active, but this does not mean it is done, providing us with glimpses into the extreme laws of physics at play. Overall, the extreme magnetic fields of magnetars shape not only their internal structure and energy output, but also define their interactions with the cosmos. Each observation reveals more about these mysterious objects and deepens our understanding of the universe's most extreme environments. Magnetars are among the most mysterious and powerful objects in space. They are a type of neutron star, which is what remains after a massive star explodes in a supernova. The leading theory for their formation revolves around the violent end of a massive star's life cycle. When such a star runs out of nuclear fuel, it collapses under its gravity, leading to an intense collapse that compresses the core to incredible densities. During this collapse, if the conditions are just right, a strong magnetic field can form, one that's millions of trillions of times stronger than Earth's magnetic field. This extraordinary magnetic field not only defines a magnetar, but also affects its behavior and lifespan. The immense pressure and rapid rotation of the neutron star can amplify the magnetic field, making it even stronger. Over time, this magnetic field can decay, releasing energy in the form of X-rays and gamma rays, which are powerful forms of radiation. This decay contributes to the characteristic bursts of light that we detect when magnetars flare. The lifespan of magnetars is relatively short when measured in cosmic terms. While neutron stars can last for millions of years, the life of a magnetar is often calculated to be just a few thousand to a few 100,000 years. This is due to the rapid depletion of their magnetic energy. As they lose energy, they exhibit less activity and can eventually fade away into relative obscurity, transitioning into a quieter state known as a normal neutron star. Magnetars are birthed from the dramatic death of massive stars, where powerful gravitational and magnetic forces combine. Their life is marked by intense activity fueled by their magnetic fields, but this vigor is temporary in the grand timeline of the universe, leading to a fascinating but short existence among the stars. Recent discoveries about magnetars, a type of neutron star with incredibly strong magnetic fields, provide new insights into stellar evolution. Traditionally, we understood neutron stars as the remnants of massive stars that have undergone supernova explosions. However, magnetars reveal a more complex and intriguing evolution process. Magnetars are characterized by magnetic fields trillions of times stronger than Earth's. This extraordinary strength can lead to powerful bursts of radiation, including X-rays and gamma rays, which illuminate their environments and give scientists valuable clues about their characteristics. These intense magnetic fields are believed to arise from the rapid rotation and collapse of massive stars, suggesting that the life cycle of a star can lead to much more than simply a neutron star. The study of magnetars helps refine our models of what happens after a star exhausts its nuclear fuel. It challenges the idea that all neutron stars simply cool down over time. Instead, it suggests that a magnetar might be in a younger phase of a neutron star's life, driven by its magnetic processes that impact its evolution. Even more, the presence of a magnetar can influence surrounding matter, causing fascinating changes in nearby stars and gas clouds. As researchers learn more about these energetic objects, it opens doors to new theories regarding the last stages of stellar life. They not only help us understand how massive stars end, but also demonstrate how unique factors, like magnetic fields, can lead to an array of outcomes in the universe. This evolving knowledge enriches our comprehension of how varying elements like mass and rotation can shape the destinies of stars and the cosmos as a whole. Magnetars, which are a special type of neutron star with incredibly strong magnetic fields, hold the key to unlocking several cosmic mysteries that intrigue scientists. First, they are considered laboratories of extreme physics. Their intense magnetic fields are billions of times stronger than those of typical magnets found on Earth. This allows researchers to study how matter behaves in extreme conditions that cannot be replicated on our planet. One of the significant mysteries magnetars could help solve is the nature of matter under such immense pressures and densities. In the core of a magnetar, matter is so compact that it's practically a soup of neutrons. Understanding how material behaves in this state can provide insights into the fundamental forces that shape the universe. Furthermore, magnetars are known for their explosive bursts of energy, which can be detected as soft gamma-ray repeats. Each burst offers a glimpse into the processes occurring within these stars and helps scientists learn about the dynamics of stellar evolution. By studying these bursts, researchers can deepen their understanding of how and why these powerful flares occur, which may also inform theories about supernova explosions. Additionally, magnetars are linked to the behavior of gravitational waves, the ripples in space-time created by massive objects in motion. Detecting events tied to magnetars may help refine our knowledge about these waves' properties, contributing to the field of gravitational wave astronomy. Magnetars serve as a bridge to understanding complex themes in astrophysics, from the states of matter at extreme densities to the energetic processes that govern some of the most violent events in the cosmos. Each discovery related to these extraordinary stars opens new avenues for understanding the fundamental laws of the universe. Pulsars are a unique type of neutron star that stand out due to their remarkable behavior. To understand this distinction, we first need to look at what a neutron star is. After a massive star reaches the end of its life and has undergone a supernova explosion, the core compresses under gravity, becoming incredibly dense. A neutron star is formed, composed mostly of neutrons packed together tightly. What makes pulsars special is their rapid rotation and the magnetic fields that accompany them. As a neutron star spins, it also has a strong magnetic field generated by the motion of charged particles within it. In pulsars, this magnetic field is tilted relative to the rotation axis. Because of this tilt, beams of radiation, like powerful lighthouse signals, are emitted from their magnetic poles. As these beams sweep through space, if they pass by Earth, we detect them as pulses of radiation at regular intervals. This is why they are called pulsars, short for pulsating stars. Some pulsars can rotate hundreds of times per second, creating a consistent pattern that can be observed across vast distances. Pulsars differ from other neutron stars in that not all neutron stars are observed to pulse. Many neutron stars do not have the necessary alignment or may not be rotating at such high speeds, so they don't exhibit this pulsing behavior. Moreover, pulsars can be used as precise cosmic clocks due to their regular pulses, which allows astronomers to explore the structure of space-time and test theories of physics. This combination of rapid rotation, strong magnetism, and periodic emissions truly sets pulsars apart in the vastness of the universe. The discovery of pulsars marked a significant milestone in the field of astrophysics. In the late 1960s, a young British astronomer named Jocelyn Bell Burnell was working on her doctoral research. As she analyzed radio waves collected from the sky using a large radio telescope, she noticed a series of regular pulsing signals. These signals were incredibly consistent, occurring at precise intervals, almost as if they were a form of cosmic ticking. Initially, Bell Burnell and her colleagues thought they might be picking up signals from extraterrestrial beings, leading to the playful nickname LGM, standing for Little Green Men. However, as more of these signals were detected, it became clear they were not of artificial origin. The pulsations were instead linked to a new type of celestial object, which came to be known as pulsars. The identification of pulsars had a profound impact on astronomers and their understanding of the universe. Pulsars are rapidly rotating neutron stars that emit beams of radiation out into space. As these beams sweep across the Earth, they create the pulses detected by radio telescopes. The discovery opened up a new field of study, providing insights into the life cycles of stars, the properties of matter in extreme conditions, and the behavior of gravity and space-time. Pulsars also became invaluable tools for testing theories of physics, helping confirm predictions about general relativity. Furthermore, the precise intervals of the pulsations allow scientists to explore the universe's vast distances and even detect gravitational waves. Overall, the discovery of pulsars shifted paradigms in astrophysics, unveiling a new realm of phenomena and revealing the complexity of our universe. Pulsars are remarkable cosmic beacons that play a crucial role in our understanding of the universe and its fundamental laws. These are highly magnetized, rotating neutron stars that emit beams of radiation, which we observe as regular pulses, much like the ticking of a cosmic clock. The precision of these pulses makes them incredibly valuable for a variety of scientific investigations. As pulsars spin, their beams sweep across space. If Earth lies in the path of one of these beams, we perceive a rhythmic signal. This reliable timing allows scientists to study everything from the nature of gravity to the behavior of materials under extreme conditions. One area where pulsars shine is in testing the principles of Einstein's general theory of relativity. For instance, the timing of pulsar signals can help scientists observe how gravity affects light and the flow of time, particularly when pulsars are part of binary systems, where two stars orbit each other. In addition to studying gravity, pulsars can help in the quest to understand the nature of dark matter and the behavior of matter in extreme environments. Because neutron stars are formed from supernova explosions, they are incredibly dense, containing a mass greater than the Sun compressed into a sphere only a few kilometers across. This density allows researchers to study the equations that govern matter at such extreme levels, pushing the boundaries of physics. One of the most exciting applications of pulsars is their potential to detect gravitational waves. These ripples in the fabric of space-time are caused by massive objects in motion, such as merging black holes. By monitoring changes in the timing of pulsar signals, scientists hope to observe these waves directly, providing deeper insights into the processes and events shaping our universe. Pulsars are not just fascinating phenomena, they serve as essential tools in the ongoing exploration of fundamental physical laws. By offering unique insights into gravity, extreme matter, and even cosmic events, pulsars help astronomers piece together the grand puzzle of the universe. Binary pulsar systems present a remarkable opportunity to explore the nature of gravity in ways that other celestial objects cannot. In these systems, two neutron stars orbit around each other, and one of them emits beams of radio waves, detecting them like a lighthouse does with light. As the stars move, the changing distance between the observer on Earth and the pulsar alters the timing of the received signals, creating a pattern. These tiny variations in timing can provide data that is incredibly precise. Scientists can measure how gravity affects the orbit of these pulsars based on the laws of gravity proposed by Einstein. When two massive objects are close to each other, their gravitational fields interact in complex ways. By observing the binary pulsar, researchers can actually see this interaction in action. One of the key discoveries from studying these systems is the conformation of gravitational waves. As the two neutron stars spiral closer together, they emit ripples in spacetime. These are gravitational waves. The precise timing measurements allow scientists to confirm predictions made by Einstein's general relativity about how these waves carry energy away from the system, causing the stars to move closer together over time. Additionally, binary pulsars help scientists test the effects of strong gravitational fields on the behavior of time. Here, time moves slower in a strong gravitational field, a concept known as time dilation. By carefully measuring how time flows for the pulsar in relation to its companion, researchers deepen our understanding of gravity under extreme conditions. Binary pulsar systems serve as natural laboratories for testing and verifying the truths of gravitational physics, providing empirical evidence for theories that describe the very fabric of our universe. Pulsars are among the most fascinating objects in the universe, acting as cosmic lighthouses that emit beams of radiation. Researchers are actively exploring various aspects of these neutron stars to deepen our understanding of their nature and implications. One major focus is the study of their emissions to better grasp the mechanisms that create their rhythmic signals. By observing these signals with advanced telescopes, scientists can uncover details about the pulsar's magnetic fields and rotation speeds, which often offer clues about their violent formation processes. Another significant aspect of ongoing research involves looking at pulsars as tools for studying fundamental physics. Scientists are investigating how pulsars can help test theories of gravity, especially in extreme conditions. Some research is directed at using array systems of pulsars to detect gravitational waves, which are ripples in spacetime caused by massive celestial events. This method could open up a new window into the universe's most energetic occurrences. There's also a growing interest in understanding how pulsars can help researchers probe the interstellar medium. As pulsar signals travel across vast distances, they can be affected by the material between them and Earth. By studying the changes in signals, scientists can gain insights into the distribution, density, and composition of this interstellar matter. Additionally, investigations are underway into millisecond pulsars. These ultra-fast spinning stars can provide significant insights into the behavior of matter under extreme conditions. Studies focused on their environments may reveal more about the dynamics of binary systems, where two stars orbit each other, and they could even lead to discoveries regarding the existence of exotic states of matter. Overall, research on pulsars is multifaceted, encompassing astrophysics, fundamental physics, and cosmology, all aimed at unraveling the mysteries of the universe through these remarkable cosmic beacons. Quantum cosmology is an area of scientific study focused on understanding the universe at its very beginning, using principles from both quantum physics and general relativity. At the core of quantum physics is the idea that particles behave in surprising and sometimes odd ways, where they can exist in multiple states at the same time and do not always follow classical rules. In contrast, general relativity describes gravity and large-scale structures, such as galaxies and planets, showing how massive bodies influence the fabric of space and time. The challenge arises because these two theories operate in different realms. While general relativity effectively explains how large objects interact and bend spacetime, it struggles to account for phenomena at the atomic or subatomic levels, where quantum physics reigns. Quantum cosmology attempts to unite these two perspectives, particularly when considering events like the Big Bang, where both quantum effects and gravity played crucial roles. Think of it like trying to understand a dance where every move influences the next. In quantum cosmology, researchers explore how the quantum behavior of tiny particles might have shaped the early universe, and how this quantum nature can be reconciled with the smooth, predictable structures described by general relativity. By examining the universe's beginnings through this quantum lens, scientists hope to reveal insights about its formation, its evolution, and the fundamental laws governing it. This quest for a unified understanding aims to provide a more complete picture of how our universe exists and operates, potentially answering some of the deepest questions about existence itself. Quantum cosmology theories offer fascinating insights into the universe's creation, focusing on the smallest scales of existence, those of particles and their behaviors governed by the laws of quantum mechanics. Imagine the universe starting as an incredibly tiny point, where space and time as we know them didn't yet exist. This initial state can be thought of as a superposition of countless possibilities, much like how a spinning coin exists as both heads and tails until it lands. In this framework, instead of a single moment of creation, the universe emerges from a complex interplay of quantum fluctuations. These fluctuations can create bubbles of spacetime that expand, leading to the formation of different regions of the universe, each with its own unique characteristics. This scenario suggests that our universe is just one of many, often referred to as a multiverse, where countless other universes also unfold, each having potentially different laws of physics. Another aspect to consider is how the concept of time itself behaves differently in quantum cosmology. Near the beginning of our universe, time may not have flowed in a linear way, allowing for the existence of multiple timelines and realities. These ideas challenge our traditional views, suggesting that the birth of the universe was a much more fluid and dynamic process than a simple explosion. Overall, quantum cosmology provides a revolutionary perspective, suggesting that creation is not merely an event, but rather an ongoing interplay of possibilities at the most fundamental level of existence, reshaping how we understand our universe's origins. Quantum cosmology explores the universe's earliest moments and seeks to merge the principles of quantum mechanics with the vast scales of cosmology, where our universe's behaviors are shaped by gravity. One significant challenge arises from the very differences in how these two realms operate. Quantum mechanics describes the behavior of tiny particles and their interactions, often filled with uncertainty and probability. On the other hand, cosmology looks at the universe as a whole, where classical rules dominate, particularly when examining gravity. Another hurdle is the difficulty in applying our understanding of quantum mechanics to the singularity of the Big Bang. At this point, our current laws of physics break down, making it incredibly hard to comprehend what truly happened. Scientists struggle with the idea that space and time themselves could behave differently under these extreme conditions. Additionally, bridging these theories requires new frameworks that can account for both the unpredictability of quantum events and the large-scale forces that shape the universe. Current models, such as string theory or loop quantum gravity, attempt to reconcile these two worlds, but they still have many unanswered questions. The need for experimental confirmation of these theories adds another layer of complexity, as we currently do not possess the technology to test conditions found at the dawn of time. The challenge lies in synthesizing these two vastly different realms of physics into a cohesive theory that can comprehensively explain the origins and evolution of the universe, while also standing up to observational scrutiny. This pursuit not only pushes the boundaries of our understanding, but also invites new ideas and methods, driving the quest for knowledge about our universe forward. Quantum cosmology is an area of science that blends the principles of quantum mechanics with the large-scale structures of the universe. It aims to unfold the mysteries of how our universe came into existence and how it behaves at both the smallest and largest scales. One of the most intriguing implications of quantum cosmology is how it reshapes our understanding of time and space. In traditional views, space and time are seen as fixed stages where events occur. However, quantum cosmology suggests that these elements might not be as solid as we once thought. Imagine a stage that can shift and change as the play unfolds. In the context of our universe, this means that space and time are intertwined with the particles and fields that make up everything around us. They can fluctuate and evolve, influenced by the behaviors of the tiniest particles. This perspective raises the possibility that time itself could be a byproduct of other fundamental processes. Instead of existing as a separate entity, time might be something that emerges from deeper interactions at the quantum level. Such a notion implies that the passage of time is not uniform, but could vary depending on the conditions present in different regions of spacetime. Moreover, quantum cosmology opens the door to understanding events like the Big Bang from a different lens. It hints that the birth of the universe may not have been a singular point in time, but a complex event shaped by the interactions of quantum fields. This could redefine how we think about the beginning and the eventual fate of everything. By blending the vastness of cosmology with the peculiar behaviors of quantum mechanics, we glimpse a universe that is dynamic and filled with potential. Our conventional notions of beginnings, endings, and the flow of time may need significant revision, giving us a fresh and exciting framework for exploring the fundamental nature of reality. As scientists continue to probe this intricate tapestry, the implications for time and space could further revolutionize our understanding in ways we are only beginning to comprehend. Recent advancements in technology and theoretical understanding are significantly shaping the landscape of quantum cosmology research. At its core, quantum cosmology seeks to unite the principles of quantum mechanics with the vastness of cosmology, aiming to explain phenomena at the very beginning of the universe and how it evolved. One of the key developments has been in the realm of quantum computing. This cutting-edge technology allows scientists to perform complex calculations much faster than traditional computers. In quantum cosmology, researchers often deal with intricate mathematical models to explore scenarios from the very early universe, such as conditions at the moment of the Big Bang. With more powerful computational tools, they can simulate these conditions with greater accuracy, revealing insights that were previously unattainable. Moreover, advancements in observational technology have enhanced our ability to gather data about the universe. Sophisticated telescopes and detectors enable astronomers to measure the cosmic microwave background radiation, the afterglow of the Big Bang, with remarkable precision. These measurements can provide a wealth of information, serving as vital clues about the universe's origins and early state, which quantum cosmologists strive to understand. The interplay between theories of quantum gravity and string theory is another exciting frontier. These theories propose novel concepts that challenge our traditional ideas about space and time. Insights gained from these frameworks can lead to new interpretations and understandings of cosmic events, potentially reshaping our grasp of how the universe operates at its most fundamental level. Furthermore, collaboration across disciplines is becoming increasingly common. Physicists, mathematicians, and computer scientists are working together to tackle the challenges in quantum cosmology. This diverse approach fosters innovation, allowing scientists to tackle once intractable problems in fresh and inventive ways. As these advancements continue to unfold, the future of quantum cosmology research looks promising. The combination of enhanced computational power, precise observational data, breakthrough theoretical insights, and interdisciplinary collaboration will likely lead to deeper understanding of the universe's mysteries and its origins. This journey into the quantum underpinnings of cosmology not only expands our knowledge, but it may also alter how we perceive reality itself. Gravitational lensing is a fascinating phenomenon that occurs when a massive object, such as a galaxy or cluster of galaxies, bends the light coming from a more distant object. Imagine shining a flashlight through a curved glass. The light won't travel in a straight line anymore. Instead, it changes direction depending on the shape of the glass. In this case, the massive object acts like that glass, using its gravity to warp the space around it. As light from a distant star or galaxy passes near this massive object, the gravitational pull alters its path. This bending effect can create multiple images of the same distant object, magnify its appearance, and even distort its shape, much like a funhouse mirror. For astronomers, this provides a unique opportunity to study objects that would otherwise be too faint or far away to see. When looking through a lens, details can be magnified, giving scientists deeper insights into the structure and makeup of distant galaxies. Observing how light behaves under the influence of gravity helps researchers learn about the distribution of dark matter, an invisible component of the universe that makes up most of its mass. Gravitational lensing thus becomes a powerful tool in the hands of astronomers. It not only enhances our view of the cosmos, but also reveals properties of the universe that would remain hidden without this extraordinary spectacle of light bending, allowing us to explore the vast expanse of space with renewed clarity. Gravitational lensing occurs when light from a distant object, like a galaxy or a star, bends as it passes near a massive object, such as another galaxy or a cluster of galaxies. Imagine looking through a clear glass of water. When you look through it, everything appears distorted. In the universe, massive structures act like that glass, manipulating the paths of light due to their strong gravitational pull. This bending of light allows astronomers to see objects that are otherwise hidden behind these massive foreground structures. By studying how much light is bent and the resulting image of the distant object, scientists can infer the mass of the object responsible for the lensing effect. This is crucial because it allows researchers to map out where dark matter is located. Dark matter is a mysterious substance that doesn't emit light and cannot be seen directly. However, it makes up a significant part of the universe's total mass. By using gravitational lensing, scientists can observe the influence of dark matter. They look for patterns in how light is distorted, which reveals the gravitational pull exerted by unseen mass. The greater the distortion, the more massive the object, and when these effects are analyzed across the cosmos, they paint a picture of dark matter's distribution. Essentially, gravitational lensing acts as a cosmic flashlight, illuminating areas affected by dark matter. It allows researchers to create maps that show not only how much dark matter exists, but also where it is concentrated, helping to deepen our understanding of the universe's structure and evolution. This tool is crucial for unraveling the mysteries behind one of the most fundamental questions in modern astrophysics. How does dark matter influence the galaxies we see and their arrangement in space? Gravitational lensing is a fascinating phenomenon that occurs when a massive object, like a galaxy or black hole, distorts the light coming from objects behind it. Scientists are eager to harness this effect to unlock several mysteries of the universe. One of the key areas of interest is understanding dark matter. This invisible substance makes up a significant portion of the universe's total mass, yet it doesn't emit light. By observing how light bends around galaxies, researchers can infer the presence and distribution of dark matter. Another mystery that gravitational lensing can help reveal is the nature of dark energy. Dark energy is believed to be responsible for the accelerating expansion of the universe, but its properties remain elusive. Observing the light from distant galaxies as it is magnified and distorted can provide insights into how dark energy interacts with the expansion of space. Additionally, scientists aim to study the formation and evolution of galaxies. By examining how light is bent around clusters of galaxies, they can piece together how these massive structures grow over time. This lensing provides a snapshot of the universe at various stages of its evolution, allowing us to trace back its history. Gravitational lensing also serves as a tool for observing distant exoplanets. When a star and its planet align with a distant background star, the gravitational pull from the planet can cause a temporary brightening of the background star. This effect can help scientists detect and study worlds beyond our own solar system, expanding our understanding of planetary formation and the diversity of celestial bodies. Gravitational lensing is a powerful method that can illuminate the hidden aspects of our universe, revealing clues about dark matter, dark energy, galaxy formation, and the search for exoplanets. Each discovery helps build a clearer picture of the cosmos and our place within it. Gravitational lensing is a fascinating phenomenon that occurs when a massive object, like a galaxy or a cluster of galaxies, bends the light coming from objects that are much farther away. You can think of it as a cosmic magnifying glass. When a massive object is positioned between us and a distant galaxy or quasar, it distorts and amplifies the light from that more remote source. This bending of light allows astronomers to better observe distant celestial bodies that we might not usually see clearly due to their great distance or inherent faintness. As the light is magnified, it provides clearer images and valuable information about the characteristics and composition of these galaxies and quasars. For instance, scientists can study the shapes, structures, and brightness of these distant objects, which helps us understand their formation and evolution over billions of years. Additionally, gravitational lensing can reveal details about the lensing object itself. By analyzing how light is distorted, researchers can gather insights into the mass and distribution of matter in the lensing galaxy. This includes understanding both the visible matter, like stars and gas, as well as dark matter, which does not emit light but has a significant gravitational effect. Moreover, gravitational lensing allows us to probe the very early universe. Light from the most distant quasars we observe today has taken billions of years to reach us. As it travels, it may encounter various gravitational fields, providing us with a layered understanding of the universe's evolution and structure. Each lensing event acts as a natural experiment, giving astronomers a way to test theories about the cosmos and refine our understanding of fundamental physics. Gravitational lensing opens a window to the far reaches of the universe, enhancing our ability to study not just distant galaxies and quasars, but also the very fabric of space itself. This tool in modern astronomy continues to reshape our perspective on the universe, unveiling its complexities and expanding our knowledge of cosmic phenomena. Gravitational lensing has revolutionized our understanding of the universe by using the bending of light caused by massive objects to gain insight into distant galaxies and cosmic structures. Imagine a massive galaxy sitting between Earth and a more distant source of light. As light from that distant source travels toward us, the galaxy's gravity essentially acts like a lens, bending and magnifying the light. This effect allows scientists to look deeper into space than ever before. One of the most significant outcomes of gravitational lensing is the ability to study dark matter. Although dark matter cannot be seen directly, its presence can be inferred from how it influences the light paths of objects behind it. By analyzing the patterns and distortions of light, researchers can map out where dark matter exists, offering clues about this mysterious substance that makes up a large portion of the universe's mass. Additionally, gravitational lensing aids in discovering exoplanets. Light from distant stars can be magnified and brightened when a planet passes in front of or near a background star. Observing these temporary spikes in brightness helps astronomers detect planets that would otherwise go unnoticed, expanding our understanding of planetary systems beyond our own. The technique also provides valuable insights into the expansion of the universe. By studying lensed images of distant supernovae, astronomers can gather data about their brightness and distance. This information helps refine measurements of the expansion rate of the universe, enhancing our understanding of cosmic dynamics. Gravitational lensing opens up a window to peer into the vast distances of the universe, revealing the hidden structures of dark matter, enabling the discovery of new exoplanets, and allowing us to explore the universe's expansion. Each of these breakthroughs not only sharpens our view of the cosmos, but also shapes the way we think about fundamental concepts in astrophysics. Preparing for communication with extraterrestrial civilizations involves a mix of science, technology, and creativity. First, scientists are focused on establishing which methods might be most effective for sending messages across vast distances in space. One approach could involve radio waves, which are already being used to send signals out into the cosmos. These waves can travel long distances without interference, making them an ideal medium for contact. Next, it is essential to create a universal language that could bridge the gap between Earth and other intelligent beings. Since we cannot assume that extraterrestrial civilizations share our languages or even our understanding of communication, scientists suggest using mathematical concepts as a foundational element. Mathematics is often seen as a universal language, capable of conveying ideas through patterns, sequences, and structures that might be recognizable by any intelligent species. For instance, sending simple prime numbers or the basic principles of geometry might serve as an introduction to our understanding of the world. Once a method of communication is chosen, sending a message is just the beginning. Scientists must also consider how to interpret the responses we receive. This means developing systems for analyzing and understanding signals that might come from outside our own planet. Any reply we receive could be a mixture of sounds, visuals, or even coded information, requiring careful study. In addition to technology, we must prepare culturally and psychologically for the possibility of encountering alien intelligence. This preparation involves open-mindedness and collaboration among global communities. People must understand that communication with extraterrestrial beings could challenge our perceptions of life and ourselves. Moreover, ongoing efforts in the field of astrobiology help us understand how life could develop in different environments, expanding our expectations of what extraterrestrial civilizations might look like and how they might communicate. Preparing ourselves not only technologically and scientifically, but also socially and mentally, may be crucial in making first contact a meaningful interaction. Preparing to communicate with alien civilizations involves choosing effective methods of sending messages, creating a universal language based on mathematics, establishing systems for decoding responses, and fostering a collaborative human approach ready to embrace the unknown. As we continue exploring the universe, the key lies in our capacity to venture into this great unknown with curiosity and respect for life in all its forms. When it comes to the possibility of contacting alien life forms, scientists and organizations have established some important protocols designed to guide our responses. These protocols aim to prepare humanity for potential first contact with an intelligent extraterrestrial civilization. One of the key frameworks in this area is known as the First Contact Protocol. This set of guidelines emphasizes the need for caution and thorough scientific evaluation before making any public announcements. The idea is to prevent panic or misunderstandings about the nature of the contact. For instance, if we were to receive a signal from another civilization, scientists would first analyze the signal to confirm its origin and determine if it is truly artificial rather than natural. Furthermore, international cooperation plays a significant role in these protocols. Organizations like the United Nations have discussions about how to handle such scenarios, emphasizing the importance of a collective response from all countries to ensure a unified and responsible approach. This cooperation is vital because any information or communication with alien civilizations would have implications for all of humanity. Astrobiologists and astronomers also follow certain practices when it comes to detecting possible extraterrestrial signals. They often use radio telescopes to monitor the skies, searching for signals that stand out from the cosmic background noise. If a potential signal is detected, it must be verified by multiple observatories to rule out any terrestrial interference before sharing the discovery with the wider scientific community. Moreover, scientists have developed guidelines for how to respond to potential messages from extraterrestrial intelligence. These guidelines emphasize transparency and thoughtful deliberation, ensuring that the messages sent back respect the unknown civilization's culture and intentions. The protocols for potential contact with alien life involve careful analysis, international cooperation, and a phased approach that emphasizes both transparency and caution. This structured response not only reflects our hope for discovery, but also showcases our commitment to handling such monumental events responsibly. The idea of interacting with extraterrestrial beings raises significant scientific and ethical considerations that are both fascinating and complex. On the scientific front, the discovery of intelligent life beyond Earth could transform our understanding of biology, evolution, and the origins of life. It would prompt scientists to rethink our definitions of intelligence and consciousness. Researchers would likely study the physiology and communication methods of these beings to learn how life can adapt to diverse environments, potentially uncovering new technologies or medicines in the process. However, this interaction is not without risks. The potential for misunderstandings or conflicts arises when two vastly different cultures or forms of intelligence meet. There is also the possibility of biological contamination, where life forms could unintentionally bring diseases to Earth or vice versa, leading to devastating consequences. These fears reflect the notion that, while the exploration of other worlds may hold great promise, it also carries significant uncertainties. Ethically, the questions deepen further. If we were to encounter extraterrestrial beings, we must consider their rights and autonomy. Are they entitled to the same moral considerations we afford to other sentient beings on Earth? The implications of making contact could lead to debates about exploitation or manipulation of these beings for our own benefits, bringing humanity's history of colonialism into question. The responsibility to ensure that interactions are respectful and mindful of the sentient nature of these beings would be paramount. Moreover, the public and governmental reactions could be unpredictable. Would we embrace this discovery as a unifying moment for humanity, or would fear and paranoia take over, leading to international tensions? The collective response to extraterrestrial contact could shape our societies in profound ways. The interaction with extraterrestrial beings contains both scientific curiosity and moral dilemmas. It presents an opportunity to enhance our understanding of life, yet it simultaneously challenges us to confront our ethics as we navigate the unknown. This unknown frontier requires us to be diligent in our exploration and sensitive in our approach to potential cosmic neighbors. Imagine encountering an alien intelligence, a civilization with knowledge beyond our wildest dreams. The impact of such collaboration could be revolutionary. Merging our understanding of science with theirs could lead to innovations we cannot yet conceive. For instance, they may have mastered energy production in ways we have yet to explore, perhaps harnessing stellar power or manipulating materials at an atomic level. Working together could accelerate breakthroughs in technology. This partnership might produce new forms of transportation that allow us to traverse vast distances in space effortlessly. It could lead to advancements in medicine, where alien insights into biology offer solutions to diseases that have long plagued humanity. Furthermore, sharing insights on artificial intelligence could propel our own systems beyond current limitations, evolving them to perform complex tasks with unprecedented efficiency. The exchange of ideas could foster a cultural renaissance, revolutionizing not just technology, but also our approach to ethics, philosophy, and the understanding of our place in the universe. Imagine a world where our limitations fade against the backdrop of shared progress, where collaboration with beings from another world inspires innovative ideas and technologies that enrich our existence and broaden our horizons. The potential for growth and discovery could reshape our civilization in ways we can only dream of today, igniting an eternal quest for knowledge and understanding that extends well beyond our planet. Establishing and nurturing relationships with extraterrestrial civilizations presents a range of complex challenges. At the onset, one of the most significant hurdles is communication. Engaging with an alien society means overcoming language barriers and cultural differences that are likely beyond our current understanding. We can't rely on human languages or expressions. Instead, we would need to find fundamental ways to convey ideas and emotions, possibly through mathematics, music, or visual representations. Another challenge is the vast distances involved in the cosmos. Space is immense, and even if we discover other civilizations, reaching them or receiving their messages could take an incredibly long time. For instance, light, being the fastest thing in the universe, still takes a considerable duration to traverse the distances between stars. This delays any form of interaction, making real-time communication virtually impossible. There's also the question of mutual interest. For a fruitful relationship, both sides must find value in engaging with each other. An extraterrestrial society might not even be aware of our existence, or perhaps they view us as insignificant. Moreover, differing technological levels could lead to skewed perceptions. Advanced civilizations may not see the need to interact with less developed ones. Trust poses another significant hurdle. We must consider the potential for misunderstanding or mistrust stemming from our intentions, values, and actions. History shows that first encounters among human societies have not always gone well, often leading to fear or hostility. If an extraterrestrial civilization perceives us as a threat rather than allies, peaceful interaction could be jeopardized. Additionally, ethical considerations arise when interacting with alien life forms. How do we respect their autonomy, their culture, and their existence? Any form of interference could lead to unintended consequences that could harm the other society or ours. Finally, the unpredictability of technological advancements adds a layer of complexity. As we move forward in our developments, the methods we might use to initiate contact could evolve, raising questions about whether those methods are responsible or appropriate. Navigating these challenges requires careful thought, openness to new ideas, and a commitment to peaceful coexistence. As humanity looks to the stars, the hope is to forge bonds that could enhance our understanding of the universe and each other. Human space exploration has profoundly changed our understanding of the universe and its many mysteries. When we first ventured beyond Earth, our primary goal was to break free from our planet's atmosphere and see what lay beyond. This pioneering spirit has since evolved into a detailed exploration of our solar system and beyond, offering crucial insights into the nature of space, time, and our own existence. When astronauts journey to space, they conduct experiments that are impossible to replicate on Earth. For example, in the weightlessness of space, researchers can study phenomena like fluid dynamics and material properties without the interference of gravity. These discoveries have not only advanced scientific knowledge, but have also led to practical applications in technology, medicine, and industry. One of the most significant contributions from space exploration is our enhanced understanding of other celestial bodies. Missions to the Moon and Mars have provided direct samples of lunar soil and Martian rocks, revealing secrets about their formation and the geological processes at play. By studying these materials, scientists can piece together a timeline of our solar system's history, informing us about its age, the evolution of planets, and the conditions necessary for life. Space telescopes like the Hubble Space Telescope allow us to observe distant galaxies and cosmic phenomena. By capturing light that has traveled millions or even billions of years, these tools have opened a window into the distant past, helping us learn about the formation of stars, the behavior of black holes, and the vast structure of the universe itself. This observational data enhances our understanding of fundamental concepts such as gravity and dark matter, which still remain elusive mysteries. Moreover, human space exploration helps to inspire a sense of wonder and curiosity. As we gaze into the cosmos, we are reminded of our place in it, not just as inhabitants of Earth, but as part of a much larger universal tapestry. Each mission, each discovery, invites deeper questions about existence, the possible existence of life elsewhere, and the future of humanity in space. Our efforts to explore beyond the confines of our planet have turned what once were abstract questions into tangible explorations. From understanding the building blocks of life to revealing the intricate mechanisms of the cosmos, human space exploration continuously fuels our quest to unravel the universe's profound mysteries. Space telescopes and probes have revolutionized our understanding of the universe. One of the most significant discoveries is the confirmation of the existence of exoplanets, which are planets outside our solar system. Using instruments on telescopes like the Kepler Space Telescope, scientists have found thousands of these distant worlds, expanding our knowledge of planetary systems and their potential for supporting life. Another groundbreaking realization was the detection of cosmic microwave background radiation, which is the afterglow of the Big Bang. This ancient light provides a snapshot of the early universe, helping researchers understand its formation and evolution. Telescopes like the Hubble Space Telescope have played a crucial role in this discovery, offering insights into the structure of galaxies and the expansion of the universe. Space probes, like Voyager, have also brought us incredible discoveries. They have traveled beyond our solar system and sent back detailed information about the outer planets, including Jupiter's complex weather and Saturn's stunning rings. This has deepened our appreciation of the diversity of planetary features and atmospheres. Additionally, the study of dark matter and dark energy has been transformative. Observations from telescopes have revealed that most of the universe is made up of materials we cannot see. This has changed the way scientists think about the cosmos, leading to a greater understanding of its mysterious expansion. The exploration of our own Moon, Mars, and beyond by space probes has illuminated the history of our solar system. Missions like Mars rover have given us unprecedented views of the Martian landscape, hinting at the planet's watery past and future exploration. Each discovery builds upon the last, painting a dynamic picture of what lies beyond our planet, allowing us to ask even more profound questions about our existence in this vast universe. International space collaborations play a crucial role in expanding our understanding of the cosmos and advancing space exploration. When countries join forces, they combine resources, expertise, and technology, creating a more robust framework for scientific discovery. For instance, the International Space Station serves as a prime example of this collaboration. It brings together space agencies from various countries, enabling them to conduct experiments otherwise impossible in a single nation's lab. These partnerships allow scientists to tackle complex problems from different perspectives. By sharing knowledge, researchers benefit from a diverse set of ideas and methodologies. This diversity is particularly beneficial in fields like astronomy and planetary science, where different cultural insights can lead to innovative research directions. Moreover, international collaborations can help reduce costs significantly. Building and launching spacecraft and conducting missions require substantial financial investment. By pooling their budgets, countries can undertake ambitious projects that a single nation might find challenging to afford alone. This financing strategy enables the exploration of distant planets, moons, and even the search for extraterrestrial life. Collaboration also fosters diplomacy and peace among nations. As countries work together for a common goal, the exploration of space, they build trust and friendships that can extend beyond scientific endeavors. This shared interest creates a platform for dialogue and cooperation that can address global issues on Earth as well. Additionally, international missions often include a variety of scientific instruments and technologies supplied by different countries, enhancing the breadth and depth of the research conducted. By sharing the results of these missions openly, the global scientific community can benefit from more comprehensive data sets, leading to greater breakthroughs in understanding fundamental questions about our universe. International collaborations in space research and exploration not only accelerate scientific advancements, but also promote global cooperation and foster unity among humankind, all while unveiling the mysteries of the universe that we share. Space agencies around the world are planning exciting missions to tackle some of the universe's biggest mysteries. For instance, one significant mission on the horizon is focused on studying the origins of the universe. This mission aims to capture detailed observations of the cosmic microwave background, which is the faint glow left over from the Big Bang. By analyzing this ancient light, scientists hope to gain insights into the conditions right after the universe was born and potentially learn more about dark matter and dark energy, two elusive components that make up much of the universe but remain poorly understood. Another key mission involves exploring the outer planets and their many moons, particularly those that may harbor life. One such mission is set to visit the icy moons of Jupiter and Saturn. These moons are believed to have subsurface oceans beneath their frozen crusts. By landing on or flying by these moons, spacecraft will look for chemical signs that indicate the potential for life, expanding our understanding of where life might exist beyond Earth. Additionally, telescopes designed to observe exoplanets, planets outside our solar system, are also being planned. By studying the atmospheres of these distant worlds, scientists hope to find clues about their composition and whether they could support life. Some of these telescopes will use advanced techniques to detect the light from these planets, searching for elements like oxygen and methane, which might suggest biological processes. In short, the upcoming missions encompass a mixture of astronomical surveys, in-depth planetary exploration, and sophisticated observational technology, all aimed at unraveling the eternal questions about our universe. These endeavors not only seek to understand where we come from, but might also illuminate the possibilities of life elsewhere in the cosmos, capturing humanity's imagination as we step deeper into the mysteries of space. The quest to unravel the mysteries of the universe has profoundly shaped human culture and our inherent curiosity. From ancient times when people gazed at the stars and speculated about their meanings, to today's sophisticated space missions, our fascination with the cosmos has been a driving force in our development. This exploration ignites our imagination and challenges our understanding of who we are and our place in the vastness of space. When we look up at the night sky, we are not just observing celestial bodies, we are engaging with questions that have perplexed humanity for centuries. Different cultures have woven these wonders into myths, art, and philosophy, offering interpretations of celestial phenomena that reflect their beliefs and values. As our scientific understanding grows, these stories evolve, merging the literal with the metaphorical. New discoveries can inspire fresh questions, pushing societies to innovate in fields like technology, physics, and mathematics. Moreover, the search for answers about the universe invites collaboration across disciplines. Scientists, artists, and dreamers unite in this quest, fostering a culture of curiosity that encourages critical thinking and creativity. The excitement surrounding missions to Mars or the study of black holes instills a sense of global unity as humanity collectively invests in these endeavors. Not only do they deepen our knowledge, but they also remind us of our shared aspirations and the extraordinary possibilities lying beyond our planet. Ultimately, the pursuit to uncover the universe's secrets influences our culture by widening our perspective, enriching our narrative as a species, and reinforcing the idea that exploring the unknown is a fundamental aspect of what it means to be human.